Hey guys, tonight we walk out onto a launch pad that somehow feels both gigantic and quiet, like a cathedral built for thunder. You can almost taste the cold metal in the air. The floodlights turn the gantry into a glowing skeleton, and the rocket stands there pretending it isn't about to do something completely unreasonable. Everything around you is still, too still, because the loudest moments always start with a pause. You hear distant pumps and valves working like a slow mechanical heartbeat. Somewhere, a radio murmurs in clipped syllables, calm voices practicing calmness on purpose. And you, standing here in the dark, get that strange mix of excitement and comfort, like your brain wants to cheer, but your body wants to sink into the warmth of a blanket. So, before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. And if you're listening in bed, tell me your location and your local time in the comments. It's always kind of soothing to imagine this same night sky story traveling across different rooms, different cities, different little pockets of quiet. Now, dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. The rocket doesn't rush you. It can't. It's strapped down, surrounded by scaffolding, wrapped in cables, grounded by rules and checklists that exist because physics has zero patience for confidence. Space exploration is often sold like a heroic sprint, but the truth is more relaxing. It's a discipline of waiting, of being careful, of respecting the fact that fire behaves the same way whether you feel brave or not. You watch vapor spill from vents along the body, thin white breath against the black sky. That vapor is a clue to one of the most calming facts about rockets. Even the most powerful machines humans have ever built are basically controlled temperature problems. Cryogenic propellants, liquid oxygen, sometimes liquid hydrogen, have to be kept unimaginably cold. Liquid oxygen sits around minus 183 Celsius. Liquid hydrogen is even colder, down near minus 253. The rocket is a thermos, a pressure vessel, a plumbing maze, and a stack of careful compromises, all standing upright like it totally belongs there. And the countdown? The countdown is less a dramatic clock and more a checklist with a heartbeat. It's a story of tiny conformations, valves in the right position, tanks at the right pressure, sensors reading what they should, computers agreeing with each other. The closer you get to zero, the more the rocket becomes an argument between heat and cold, between pressure and structure, between the desire to rise and the need to not explode in a very public way. That's why launch days have holds. Plan pauses because the point isn't to be fast. The point is to be right. You can picture the earliest days when right was a rougher idea, when rockets were mostly loud guesses. The first practical liquid-fueled rockets were built by people who were equal parts dreamer and stubborn engineer. Robert Goddard, for example, launched an early liquid-fueled rocket in the 1920s that didn't go very high by modern standards, but the principle mattered. Carry your own oxidizer because air gets thin and then it just stops being there. That simple rule, bring what you need, becomes a theme that repeats through everything you're going to hear tonight, from breathing to power to navigation. And even when rocketry took a darker path for a while, the physics didn't change. The uncomfortable truth is that the technology that eventually helped lift satellites and people into orbit also grew through military programs. Space exploration is full of these moral knots. If you treat them gently, they don't ruin the mood. They just remind you that human progress is messy and the sky doesn't care how you got there. What matters for your sleepy brain is this. The same equations that once aimed a weapon later aimed a telescope. The same propulsion that once promised destruction later carried weather forecasts, rescue signals, and photographs of planets that feel like dreams. You stand by the pad and let your mind drift into what leaving Earth actually means. It isn't about going up. Planes go up. Mountains go up. Even fireworks go up, briefly, and then gravity claps politely and ends the show. Leaving Earth is about going sideways fast enough that you keep missing the ground. Orbit is a continuous fall that never quite lands, a calm idea hiding inside a violent process. There's a number that engineers whisper like a spell, roughly 7.8 kilometers per second for low Earth orbit, about 28,000 kilometers per hour. Your brain doesn't need to hold it precisely. What it needs to feel is the scale. The rocket isn't trying to reach space like it's a ceiling. It's trying to reach speed like it's a key. Height matters. Sure, air drag is annoying and heating is rude, but speed is what changes your relationship with Earth. And Earth is not easily impressed. The rocket's mass is mostly propellant. That's another calming, almost funny truth. The heroic metal tower is, in a way, a fancy container for fuel. When you see a rocket rise, you're watching it throw most of itself away on purpose. Stages separate, engines cut off, pieces fall back, because carrying empty tanks is like bringing an empty suitcase on a marathon. The staging idea seems brutal, but it's graceful in a cold, practical way. Discard what you no longer need. Keep what still has work to do. You can almost feel how many minds and hands sit inside this process. Space exploration is a team sport played across continents, with people who specialize in things you'll never see. Vibration analysis, thermal expansion, software redundancy, seal materials, lightning protection, the chemistry of propellants, the tiny details of how metal behaves when it's cold enough to change its personality. And because you're listening to this to sleep, you get to enjoy the comfort of that human effort without needing to do any of it. The pad itself is an engineered landscape. The flame trench is carved like a canal for fire because the exhaust has to go somewhere. If you just blasted it straight into concrete, the concrete would try to become a different kind of concrete in the worst way. The water deluge systems are one of the most soothing images in all of spaceflight. Huge volumes of water dumped onto the pad right at liftoff to suppress sound and protect the vehicle. Sound at launch isn't just loud. It's physically dangerous, a pressure wave that can shake components apart. So they drown the sound in water. It's like the most expensive rainstorm you've ever imagined, used as a lullaby for a machine that's about to roar. And in a way, that's the whole vibe of space exploration at its best. You don't fight nature with bravado. You work with nature by understanding it. You accept that acoustics can break hardware. You accept that vibration can shake loose a connector. You accept that heat can warp a structure by millimeters that matter more than your feelings. You accept, you measure, you adjust. The light wind shifts. You look up, and the stars don't look like decorations. They look like destinations that have been waiting longer than anything you've ever worried about. Space has this effect. It makes your personal timeline feel small without making it feel meaningless. The night sky isn't mocking you. It's inviting you to relax and to scale. You can't talk about launch pads without the first beeps and blips that made the world realize, all at once, that the sky had become accessible. Sputnik's signal, simple, repetitive, wasn't fancy science in a lab coat. It was a radio heartbeat circling Earth, something you could hear and understand even if you didn't understand orbital mechanics. A tiny object up there, moving fast, making a sound that meant the future had arrived. People listened to it with fear, with awe, with curiosity, and with the kind of attention you only give to things that change the rules of reality. Not long after, humans went too. The first human in orbit experienced something that doesn't get talked about enough. The emotional whiplash of seeing Earth as a whole. Blue, bright, fragile, wrapped in a thin atmosphere that looks like a shy glow from up there. It's not a political symbol when you're looking at it from space. It's just a fact. Everything you know is on that sphere. Every argument, every love story, every sleepy night, every time you laughed so hard you forgot to breathe for a second. All of it. But before the romance, there were the hard problems. How do you keep someone alive in a sealed capsule? How do you control orientation without wings? How do you manage heat when there's no air to carry it away? How do you come home without turning your vehicle into a meteor? Those questions pushed engineers into solutions that are both brilliant and oddly comforting because they're so practical. A spacecraft is not a magical chariot. It's a carefully managed environment with rules. Re-entry, for example, is not about coming down. It's about energy. You went up by pouring energy into speed. You come home by safely getting rid of that speed. The atmosphere becomes a brake pad, and braking produces heat. So much heat that spacecraft need thermal protection systems that sound like something from a fantasy novel, but are actually just materials science doing overtime. Heat shields ablate, meaning they intentionally burn away, carrying heat with them as they sacrifice their surface. It's strangely poetic. You return to Earth by shedding layers, by letting the outside take the punishment so the inside stays calm. You can also sense how the early space age developed a kind of quiet ritual around certainty. Redundancy became a love language. You don't trust a single sensor if you can have three. You don't rely on one computer if you can have two that cross-check each other. You don't assume a valve worked just because you told it to. You verify, and verification, repeated 1,000 times, turns chaos into something you can sleep to. The rocket's skin, whether white, black, or metallic, also tells a story. Paint and coatings aren't just for looks. Some surfaces reflect sunlight to manage heating. Some protect against corrosion. Some are chosen because they make cracks easier to spot. Even color can be a safety tool. It's funny how the simplest detail, what something looks like, can be anchored in a very serious purpose. And then there's the gentle absurdity. All this grandeur starts with tiny signals. A command to open a valve, a sensor reading pressure, a software flag flipping from standby to go. The most epic human journeys begin with small, boring data. If you're the kind of person who finds comfort in order, space exploration is basically a bedtime story written in telemetry. You're still by the pad, still listening to those calm voices on the radio, and the rocket doesn't feel like a weapon or a toy. It feels like a question. Can you build something that survives its own power? Can you aim fire so precisely it becomes transportation? Can you climb beyond the air and still keep your feet metaphorically on the ground? The answer, again and again, has been yes. Sometimes clumsily, sometimes beautifully, always at a cost, and always with the steady hum of people trying to make it safer the next time. The countdown reaches those final moments where everything tightens. The vehicle is fully fueled, chilled, pressurized, and waiting. The guidance system knows which way is up, and, more importantly, which way is sideways. The weather is watched like it's part of the engineering team. Lightning is not invited to this party. Upper-level winds are measured because a gust high above you can push on a tall rocket like a slow hand on a candle flame. And you feel your own breathing match the pace of it all. It's not adrenaline, it's alignment. You understand, in a very relaxed way, that space exploration is magnificent because it's controlled. It's not chaos winning. It's humans learning the rules well enough to move through them. There's a final quiet click in the soundscape. Maybe imaginary, maybe real, the kind of tiny sound that says a latch is secure or a system has transition states. And in that hush, you can almost hear what's coming next in the grand arc of this story. Not the roar, not yet, but the whisper that follows the roar. The moment when the rocket is already gone and you're left with radio voices and signals traveling into darkness, carrying updates back to Earth like soft, patient proof that something made it. The rocket is already a memory to your eyes, but the radio keeps it alive. That's the secret comfort. In spaceflight, the loud part is brief, and the long relationship happens through whispers. You don't really talk to a spacecraft the way you talk to a person. You send a carefully shaped signal, you wait, and you listen for a reply that's been thinned out by distance until it's almost more idea than sound. It starts close and almost friendly. In the first minutes after launch, the vehicle is still near enough that antennas on the ground can track it without breaking sweat. Telemetry pours down in streams. Temperatures, pressures, voltages, tiny status flags that say things like, "Yes, I'm fine," and "Yes, this valve did what you asked." And because engineers are engineers, fine is never just one number. It's three numbers agreeing politely, plus a backup sensor on standby in case the first two decide to start improvising. You can imagine those signals as faint threads stretching upward, holding the story together while the rocket's roar fades into the background. The first stage separation happens, and you don't hear it. You receive it. A change in acceleration, a new set of engine parameters, a different vibration signature. Space exploration is like that. The real drama arrives as data, neat and indifferent, delivered in the calm voice of physics. Then orbit settles in, and the quiet grows bigger. At this point, the spacecraft is moving fast enough that the ground can't keep a single antenna pointed at it for long. Earth rotates, the vehicle races overhead, and the link hands off from one station to another like a relay runner who never looks tired. This is where the world-spanning infrastructure starts to feel almost magical. Not because it's mysterious, but because it's so human. People built a global ear for the sky. You might picture a few giant dishes on remote hillsides, far from city noise, pointed upward like patient listeners. Some of them are part of the Deep Space Network, a name that sounds like a sci-fi club, but is really a system designed to do one humble, heroic job. Hear a spacecraft when it has wandered so far away that its signal is barely more powerful than the background hiss of the universe. Those dishes sit in 3 regions spread around the planet. California's Mojave Desert, near Madrid in Spain, and near Canberra in Australia, spaced so Earth's rotation doesn't leave a gap. One site is always able to see deep space targets above the horizon, even when the others are staring at the wrong half of the sky. It's a simple geometry trick with a profound result. Even when your spacecraft is alone in the dark, someone on Earth can usually listen. And listening is not as simple as turn up the volume. The farther a signal travels, the more it spreads out. It doesn't stay a tidy beam. It expands like ripples in a pond, and the pond is unimaginably large. That's the inverse square law, quietly stealing your signal strength. Double the distance, and your signal becomes 4 times weaker. 10 times farther, and it's 100 times weaker. Eventually, the spacecraft is sending a transmission that, when it reaches Earth, is weaker than the random static generated by the electronics in the receiving system, which is a slightly insulting way for reality to behave, but reality has never been great with customer service. So engineers fight back with cleverness instead of brute force. They use extremely stable frequencies, ultra-sensitive receivers, and antennas so big they look like they should have their own weather systems. They cool the receivers to reduce thermal noise. They narrow the bandwidth so they aren't listening to every stray whisper at once. They use error-correcting codes, which is basically teaching the message to survive damage. It's the same philosophy as redundancy on the rocket. Assume the universe will mess with your plan, then build your plan so it still works when the universe does exactly that. Error correction is one of those quietly beautiful inventions that feels made for bedtime. The spacecraft transmits data with extra structure baked in. So if some bits flip on the way, because of noise, interference, cosmic mischief, the ground can often reconstruct what was meant. It's like sending a sentence with just enough rhythm that even if a few letters smear, the meaning still arrives intact. Over the decades, space missions have used different schemes. Reed-Solomon, convolutional codes, turbo codes, LDPC, names that sound like awkward band lineups, but they all share the same purpose. Keep the story readable, even when the ink gets splashed. And then there's time, which in space becomes the slowest character in the room. In movies, mission control says something dramatic, and the astronaut replies instantly. In actual deep space, you speak and then you wait. If a spacecraft is on Mars, the one-way light time can be a few minutes or more than 20 minutes, depending on where Earth and Mars sit in their orbits. That means you can't have a normal conversation. You can't even have a normal argument. By the time your comeback arrives, everyone has forgotten what they were mad about, which honestly seems like a feature. This delay changes everything about how you operate a mission. You don't joystick a rover in real time. You send a plan. You anticipate problems. You build an autonomy so the machine can keep itself safe when no one can answer quickly. Your spacecraft becomes a cautious little professional. It watches its own temperatures, monitors its own power, and if something looks wrong, it can enter a safe mode, basically curling up and protecting itself until it can re-establish contact. Safe mode isn't glamorous, but it's reassuring. The spacecraft stops doing fancy science, points its antenna more reliably, conserves energy, and waits. It's the space equivalent of turning off all the apps on your phone because it's overheating, except your phone isn't a billion kilometers away with one chance to get it right. Even closer to Earth, time still matters. A spacecraft in low orbit may zip overhead in minutes, forcing you to schedule brief communication windows. Sometimes the vehicle can only talk to certain ground stations at certain times. So the whole system learns choreography. Commands are packed into sequences. Data is stored on board and downlinked later. And because every second on a big dish can be valuable, especially when multiple missions are competing for attention, communication becomes a kind of quiet logistics puzzle. The signals themselves are carried on radio waves, but not the old-fashioned AM station kind. Spacecraft often use specific bands, S-band, X-band, Ka-band, chosen because they balance atmospheric effects, antenna size, and data capacity. Higher frequencies can carry more data, but they can also be more sensitive to things like weather. Rain can be rude to certain lengths. The atmosphere, usually so supportive of life, becomes a mildly annoying filter for radio, which is a charming reminder that Earth always has an opinion. And because the spacecraft is moving relative to Earth, the frequency you receive is shifted slightly, a Doppler shift. It's the same effect that makes a siren change pitch as an ambulance passes, except here it's a spacecraft, and the siren is a precise carrier wave. Engineers use that shift as another kind of information. From Doppler measurements, they can infer velocity with astonishing precision. They can track a spacecraft's motion not just by where it appears in the sky, but by how its signal stretches and compresses in frequency. Distance, too, can be measured by timing how long a signal takes to travel, especially when you use specially structured ranging codes. Space navigation becomes a dance between time and frequency, like the universe is giving you a metronome and asking you to stay on beat. When the spacecraft is far enough away, pointing becomes everything. High-gain antennas are not polite wide-angle broadcasters. They are focused beams, like a flashlight rather than a lamp. That's great for reaching Earth, but means the spacecraft must aim. A tiny pointing error can drop the link. So the vehicle uses star trackers, sun sensors, gyroscopes, reaction wheels, small, elegant devices that help it know its attitude and hold its gaze steady. Reaction wheels are particularly soothing to imagine. Spinning rotors that let the spacecraft rotate without expelling propellant, conserving fuel by trading angular momentum internally. It's a quiet kind of motion, like adjusting your posture without moving across the room. And sometimes, even with perfect aiming, the universe puts a hand in the way. There are moments called solar conjunctions, when the spacecraft is nearly behind the sun from Earth's perspective. The radio signal must pass near the sun's plasma, and that plasma can scatter and distort the transmission. The link becomes noisy. Data rates are reduced. Commands may be limited or paused. Mission teams plan for these periods like sailors planning around storms. It's not catastrophic, it's just the solar system reminding you that it has weather of its own, and you are living inside it. The most strangely comforting part is how patient everyone has to be. A deep space mission teaches you to accept that you can do everything right and still have to wait. You send a command sequence, maybe a burn to adjust trajectory, and then you sit with the silence. There's no instant feedback. There's a gap where you have to trust your math and your engineering and your past discipline. And that trust isn't blind. It's earned by endless testing, by simulations, by rehearsals, by the kind of careful thinking that doesn't raise its voice. You can feel the atmosphere of a control room during those waits. Not frantic shouting, more like people holding their breath politely. Screens filled with numbers that refuse to be dramatic. A few status lights. A clock counting in a way that feels almost tender because everyone knows the signal is on its way traveling at light speed and still taking its time. And that is the weird miracle. Light speed is unimaginably fast, yet space is so unimaginably large that even light has to commute. Picture a signal leaving Earth, racing outward at nearly 300,000 kilometers per second. It crosses the orbit of the moon in a little over a second. It reaches the sun in about 8 minutes. It keeps going past Mars when Mars is in the way, past the outer planets when they're out there, and eventually it becomes a whisper stretched so thin that detecting it is like trying to hear a single person humming from the other end of the ocean. Voyager is a good anchor for that feeling. Those spacecraft are so far away that their signals arrive at Earth faint and delayed, yet still recognizable, still carrying data about their health and the space around them. Their power sources have weakened over time as their radioisotope generators produce less electricity, which means the spacecraft has to choose what to keep alive. Instruments get turned off. Heaters are minimized. Systems are managed like a slow, careful household budget. And still, a small transmitter, powered by dwindling watts, continues to speak. There's something quietly moving about that, not in a sentimental way that interrupts your sleep, but in a steady way. A machine built decades ago, drifting through interstellar space, still sending a heartbeat back to the planet that launched it. It's the opposite of disposable culture. Its patience turned into hardware. Even near missions have their own gentle drama. When a Mars lander descends, the famous 7 minutes of terror is really 7 minutes of waiting on Earth. The landing happens on Mars, fast and real and unforgiving, but the people who send it can only watch delayed telemetry. By the time they receive confirmation, the outcome already exists. The suspense is baked into the speed of light. You can't negotiate with it. You can only live with it. And that constraint, no instant control, shapes the entire character of exploration. It forces spacecraft to be competent. It forces mission planners to think ahead. It forces engineers to design systems that can tolerate uncertainty. It forces humans to accept that the universe is not interactive in the way apps are interactive, which, honestly, is probably healthier. Back on Earth, those giant dishes keep turning, smooth and deliberate, tracking targets you can't see. They listen through noise. They pull patterns out of static. They take a signal that arrives weaker than the background is and translate it into meaning. A temperature reading, an image packet, a note that a solar panel is producing power, a confirmation that a tiny thruster fired for exactly the planned duration. You don't have to know the math to feel the comfort. The comfort is in the relationship itself. Earth sending a whisper, space replying with a whisper, and the whole conversation stretched across darkness like a thin thread that never quite breaks. The last image you keep is a calm one. Somewhere far above, a spacecraft rotates slightly to point its antenna home, like turning its face toward a familiar voice. Down here, a dish in the desert listens, surrounded by quiet, hearing that voice arrive as a faint ripple in the airless ocean between worlds, and your mind follows that ripple forward because the next elegant trick, borrowing motion from planets, also begins as a whisper, a small trajectory adjustment, a tiny push, a precise choice that will later look like magic. That tiny push doesn't look heroic on a screen. A thruster fires for a few seconds, a predicted line nudges a fraction of a degree, and the only visible drama is that a room full of professionals suddenly treats the silence like it might break. The payoff arrives later, quietly, when the spacecraft glides past a planet and leaves with a different speed and a different destiny, as if the solar system casually offered a ride. This is where travel stops being about brute force and starts being about borrowing. A rocket gets you away from Earth. After that, fuel is precious, and the universe is stingy about giving you more. Gravity assists are how you negotiate with that stinginess. You approach a moving planet, fall into its gravity well, swing around, and depart on a new heading. In the planet's own frame, nothing mystical happens. You arrived and you left at essentially the same speed. The planet redirected you. But in the sun's frame, the planet itself is moving, and your path can pick up a little of that motion. A simple way to feel it is to imagine the planet as a train moving along its track. In a train's frame, you run in, bounce off a wall, and run out with the same speed you had before. But for someone standing on the ground, the train's motion adds to yours, and the bounce changes whether you leave with more or less ground speed. Planets are those trains, except the track is an orbit and the wall is gravity, and the bounce is a smooth curve that never touches anything. The geometry has a comforting logic. Approach from behind the planet, with the planet running ahead of you in its orbit, and the encounter can speed you up relative to the sun approach from in front, and the encounter can slow you down, trading speed for a different path. The same gravity can act like a boost or a brake, depending on how you show up, which feels almost like the solar system has two moods, helpful and corrective. Underneath, that is the quiet detail mission designers live with, the turning angle. How sharply the planet can bend your path depends on how close you pass and how fast you arrive. Closer means stronger gravity and a sharper bend. Faster means you spend less time under that grip and the bend is smaller. Closer also means risk. Atmospheres, rings, radiation belts, stray dust. So the closest approach is chosen with the cautious seriousness of someone placing a glass on the edge of a table and wanting it to stay there. It helps to picture the planet as a moving hill whose slopes you can surf. You don't climb and stop. You fall in, carve a curve, and leave. The curve itself is smooth. The planning is long. A gravity assist must happen when the planet is in the right place, and you must arrive at the right angle so the outgoing path points toward the next target. Miss the appointment, and the universe doesn't scold you. It simply continues. That's why launch windows can be narrow. It isn't only about the rocket or the weather. It's about the choreography of worlds. Each body keeps moving, and you're aiming in an intersection in space and time that exists only briefly. Once you accept that, the more elaborate routes start to feel natural. Some missions use several flybys not because they enjoy scenic detours, but because each encounter is a gentle nudge that substitutes for propellant they cannot afford to carry. Rosetta used multiple Earth and Mars flybys on its way to a comet. Bepi-Colombo used a chain of Earth, Venus, and Mercury flybys to reach Mercury, because arriving there with the right speed is like trying to join a high-speed parade without crashing into the float in front of you. Voyager is the classic lullaby here because it turned a rare alignment into a path. Launched in 1977, Voyager 1 and 2 used Jupiter's gravity to change speed and direction, then used Saturn's. Voyager 2 continued onward to Uranus and Neptune. The images get the headlines, but the trajectory is the truly soothing wonder. Those spacecraft were handed along, planet to planet, like a message passed down a line of moving giants. Jupiter tends to steal the spotlight because it's enormous. A close pass can reshape your orbit around the sun far more than your onboard engines could afford. Jupiter can fling you outward, tilt your path, or aim you toward a precise region of the outer solar system. The same planet that makes the solar system feel stable also makes deep travel feel possible. Cassini's route to Saturn shows gravity assists as patience stacked on patience. It used flybys of Venus, Venus again, then Earth, then Jupiter before reaching Saturn, each one changing energy and direction until Saturn became reachable with fuel left to enter orbit and stay. Messenger, headed to Mercury, used assists in the opposite emotional direction. Going inward requires shedding solar orbital energy, so you don't arrive too fast to be captured. It took repeated flybys, Earth, Venus, and Mercury itself, each one trimming the mismatch between where you are and what Mercury demands. New Horizons used Jupiter as a boost on the way to Pluto, and the flyby doubled as a rehearsal. Instruments were tested, navigation refined, and Jupiter's system offered science as a bonus. In deep travel, getting there is long enough that you might as well learn on the way. Sometimes the slingshot pairs with timing that feels like a quiet hack. A burn performed when you're moving fastest. near closest approach in a deep gravity well, can change your orbit more efficiently than the same burn performed far away at slower speed. This is the Oberth effect. The engine isn't stronger, but the moment is. A small push at high velocity can produce a larger change in orbital energy, like a gentle shove that matters most when you're already in motion. Solar missions lean into this kind of cleverness. Parker Solar Probe, built to pass astonishingly close to the Sun, doesn't dive once and hope. It uses repeated Venus flybys to reshape its orbit, lowering its closest approach step by step. Each encounter is another gentle tap that steals a bit of orbital energy and lets the spacecraft sink deeper inward, guided by the same quiet math that guided Voyager outward. All of this depends on navigation that is both fragile and relentless. A flyby happens fast at closest approach, and small errors can become large misses because distance magnifies angles. Mission teams keep listening to the spacecraft's radio signal, using time and frequency measurements to infer position and velocity, then scheduling tiny correction burns so the spacecraft threads the planned corridor with precision that feels almost unfair. During the flyby itself, the spacecraft often has to choose between looking and talking. The antenna might need to face Earth while cameras face the planet. If it can't do both, the spacecraft records data on board and speaks later, when the urgent geometry is passed. Silence becomes part of the plan, and the most spectacular moments can happen with nobody hearing them in real time. When the flyby is done, the planet falls away behind you, and your outgoing trajectory feels like a new sentence written in the language of orbits. The speed you gained is invisible, but it changes the calendar. The direction you gained is intangible, but it points you toward worlds you would not otherwise reach. And as that new path stretches ahead, another quiet truth begins to surface. These routes pass through regions where dust grains drift at high speed, where micrometeoroids don't announce themselves, and where temperature swings can be brutal. The slingshot got you moving. The next part is how you stay intact while you do. The new trajectory feels smooth in your imagination, almost effortless, and that's the trap. The solar system looks calm from a distance, but it's full of moving grit. Space isn't empty so much as it's politely sparse, and the sparsity is what makes it unsettling. In an ocean, you can at least see waves. Out here, the waves are grains of dust that don't care about your mission patch. Micrometeoroids are the small debris of natural history. Bits of comet trails, fragments of old collisions, particles that have been orbiting the sun for longer than any human language has had a word for rocket. They're often no bigger than grains of sand, sometimes smaller than a speck of pepper, and they hit like tiny bullets because of speed, not size. A spacecraft in deep space might see impacts at tens of kilometers per second. In Earth orbit, there's a second category of trouble: orbital debris, human-made fragments that can be just as small and just as fast, moving relative to you with the same kind of indifference. That speed changes your intuition. A grain of paint the size of a sesame seed, traveling at orbital velocity, carries enough energy to pit metal. A millimeter-sized fragment can punch a crater that looks larger than it has any right to look because the material it hits behaves briefly like a fluid under shock. The impact doesn't feel like a pebble tapping a window. It behaves like a moment of high-pressure physics, a fast, violent handshake that leaves a signature. And yet, the spacecraft survives. Not because it got lucky every time, though luck is definitely employed in this line of work, but because the design assumes the universe will throw sand at you. The most iconic protective look in space is that shimmering, crinkled wrapping that makes satellites resemble oversized candy. That isn't decoration. That's multi-layer insulation, MLI, and it's one of the quiet miracles of engineering because it solves two problems at once: temperature and radiation. In a vacuum, you can't rely on air to carry heat away. Heat moves primarily by radiation, and surfaces exchange infrared energy with whatever they see. If a spacecraft sees the sun, it heats. If it sees deep space, it cools. If it sees a planet, It receives thermal radiation from that planet and also reflects sunlight coming off it. The spacecraft is constantly in a negotiation about what it's facing. MLI makes that negotiation easier. It's a stack of thin layers, often plastic films like mylar or Kapton, coated with reflective metal, such as aluminum, separated so they don't conduct heat directly. Each layer reflects a portion of radiated heat, and the stack greatly reduces the net flow. That crinkly texture matters, too, because it helps maintain separation between layers and prevents them from sticking together, which would turn the stack into a heat-conducting sandwich. Sometimes the outer layer has a golden look, and people call it gold foil, which isn't always literally gold, but the vibe is accurate. It's the visual language of protection. When it is gold-toned, the color can come from materials like Kapton, which naturally has an amber hue, especially when combined with thin metallic coatings. The effect is oddly luxurious for something whose main job is to stop your spacecraft from cooking or freezing. If you ever wanted proof that elegance can be purely functional, space hardware provides it without trying. The temperature problem is relentless because space doesn't do mild. In sunlight, surfaces can get hot enough to damage electronics or warp structures. In shadow, they can plunge cold enough to make lubricants thicken, batteries lose performance, and materials contract in ways that stress joints. A spacecraft is always expanding and contracting slightly as it moves through light and darkness. That's why thermal engineers obsess over coefficients of thermal expansion and why spacecraft are full of heaters that sound boring until you realize they're preventing a mission-ending crack. Those heaters aren't comfort luxuries. They're survival tools, little electric blankets for valves and instruments that have to stay within tight temperature ranges. And because power is precious, you don't heat everything. You heat what matters most, you insulate what you can, and you radiate away excess when you have too much. Radiators are another quiet concept that becomes strangely soothing once you visualize it. A radiator in space isn't a warm metal box like the one in an old apartment. It's a surface designed to emit infrared energy efficiently. When a spacecraft needs to get rid of heat from electronics, it moves that heat through conductive paths, often heat pipes filled with fluid that evaporates and condenses in a cycle to a radiator panel that faces cold space. The radiator sees darkness and dumps heat into it. No fan, nobody's, just photons leaving, carrying energy away, disappearing into the night. That image alone can slow your breathing if you take it seriously for a moment. But insulation and radiators won't stop a fast grain of cosmic grit. For that, spacecraft use shielding, and one of the most elegant ideas is the Whipple shield. It sounds like a cartoon name, which is unfortunate because it's deeply serious. The concept is simple. Place a thin sacrificial layer in front of the main wall, with a gap between. When a micrometeoroid hits the outer layer, it breaks apart, vaporizes, or spreads into a cloud of fragments. By the time that cloud reaches the main wall, the energy is distributed over a wider area, reducing penetration. You're turning a bullet into a spray before it meets the real armor. The International Space Station uses variations of this approach because low Earth orbit is not only dusty, it's littered with human leftovers. Paint flecks, metal fragments, bits of insulation, even tiny shards created by collisions. The station's modules have protective layers to handle impacts from small debris, and crews track larger pieces so they can perform avoidance maneuvers when necessary. There's something almost comforting about that, too. A massive structure floating overhead, protected by layers and careful planning, with people inside living ordinary routines, while the outside quietly endures a sandstorm of invisible motion. Deep space has different patterns. You don't have the same density of human-made debris far from Earth, but you do have interplanetary dust and occasional higher-speed impacts. Many spacecraft carry dust detectors, not just for safety, but because those tiny hits can teach you about the environment. Dust is both threat and science target. A grain that could scar a surface can also be evidence of a comet's trail or the history of collisions in an asteroid belt. Space exploration has this habit of turning hazards into information, like it can't resist learning even when it's being inconvenienced. And then there's light. Hard, direct, merciless light. The sun is not just a bright object. In space, it becomes a design constraint, a constant presence that can blind sensors, overheat components, and create power. Solar panels are both wings and lifelines. They convert sunlight into electricity, but they also have to survive radiation, micrometeoroids, and thermal cycling. Over time, radiation can degrade solar cell performance. Engineers anticipate that and size the arrays with margin, like packing extra water for a long trip because you know thirst will happen. Radiation is another kind of invisible grit. Not the gentle, romantic starlight, but energetic particles from the sun and cosmic rays from beyond. These particles can flip bits in electronics, a phenomenon called a single-event upset. It's like a cosmic prank that rewrites one tiny piece of memory, except the joke is only funny if your software is prepared. Spacecraft computers use error detection and correction, redundancy, and radiation-hardened components to keep the mission steady. It's the same philosophy repeating again. The universe will poke you, plan to be poked. When you look at certain spacecraft, you can almost read their radiation strategy in their silhouettes. Some carry thick shielding around sensitive electronics. Some place instruments behind propellant tanks or structural elements to use mass as protection. Some accept that damage will happen and rely on fault-tolerant design. Nothing is immortal, but the goal is long enough to do the job. The most dramatic example of thermal and radiation management living in harmony is a space telescope that has to stay extremely cold while still being near a star. That sounds impossible until you remember that space engineering thrives on impossible as a hobby. A telescope observing in the infrared needs its instruments to be cold so they don't drown faint cosmic signals in their own heat. That's where a sun shield becomes more than a sheet. It becomes architecture, thin layers, carefully shaped, arranged so the side facing the sun can take the hit while the side in shadow becomes a calm, cold sanctuary. The shield blocks sunlight, reduces heating, and allows the telescope to radiate heat away into deep space. It's like holding a hand between your face and a campfire, except the hand is the size of a tennis court, and it has to unfold perfectly from a compact package without the option of a do-over. And the materials matter. Films like Captain are used because they tolerate temperature extremes and hold their properties in harsh environments. Coatings are chosen for reflectivity, emissivity, durability. Seams and tensioning systems are designed so the layers don't touch, because contact would conduct heat and ruin the effect. The engineering is meticulous, and what you get is a telescope that can sit in a stable thermal state, quietly collecting ancient photons while the sun does its loud sun thing on the other side of a barrier. That barrier isn't just a thermal trick. It's a light management trick, too. The telescope has to keep stray light from scattering into instruments, has to avoid heating that would create infrared glow. So the shield becomes part of the optical environment. It shapes darkness. Darkness in space is not simply absence. It's a resource you build. The same goes for the rest of the spacecraft. Baffles prevent sunlight from hitting sensors directly. Surfaces are treated to reduce glare. Star trackers need clean views so they can recognize constellations, not get fooled by reflections. Even the paint on a component can matter because its reflectivity determines whether it becomes a hot spot that warms nearby systems. And while all this is happening, the spacecraft is still moving through dust. Those impacts leave tiny scars, and those scars become a kind of diary. Some missions return with surfaces peppered by micrometeoroid hits, each crater a timestamp of a nearly invisible event. The funny part is how small those scars look compared to the enormity of the travel. A journey across millions or billions of kilometers, and the evidence can be a pinprick. It makes you respect scale in a new way. The vastness is not empty, it's delicate. Tiny particles can matter. Tiny temperature shifts can matter. tiny bits flipping in memory can matter. Space exploration isn't only about big rockets and big planets. It's about small things behaving with outsized consequences because the environment offers no cushioning. And yet, despite the harshness, there's a softness in the way engineers respond. They don't try to dominate space. They wrap their machines in reflective blankets, build sacrificial layers, route heat with silent fluids, teach computers to forgive a flipped bit, and then they send these fragile, protected instruments on paths shaped by gravity and patience. By the time you picture the spacecraft gliding onward, protected by its shimmering skin and quiet armor, the earlier slingshot feels even more impressive. It wasn't just a clever shortcut. It was a commitment to long travel through a place that will constantly test you with tiny collisions and huge temperature swings. The next question becomes inevitable, almost intimate. If the outside is this unforgiving, how do you keep the inside, especially the human inside, stable, breathable, and calm? You start to notice how quickly your mind wants to romanticize the outside of the spacecraft. The shimmering insulation, the tidy radiators, the brave little shields taking sand grain hits at ridiculous speeds. But the moment you imagine a human inside, the romance gets replaced by something much calmer and more intimate. Air, water, warmth, and the quiet discipline of keeping biology from having opinions. Spaceflight is often described like it's about conquering distance, yet the first real victory is smaller. It's making a pocket of Earth that doesn't leak. On the ground, you never think about the atmosphere as a resource you're spending. You borrow it freely. You exhale into an endless supply. You breathe back an endless supply. In a spacecraft, every breath becomes part of closed loop, and the loop becomes a mission. You can have the best navigation in the solar system and the most elegant gravity assist, and none of it matters if your cabin turns into a slow chemistry problem. So the air is managed like a living budget. Oxygen has to stay within a narrow range. Carbon dioxide has to be kept low enough that it doesn't make your head feel heavy. Humidity has to be controlled so you don't end up with a damp floating rainforest and trace chemicals. The weird little byproducts of plastics, electronics, cleaners, and humans simply existing have to be filtered because your nose can't vote on cabin safety. A spacecraft cabin is not fresh air. It's curated air. The first comforting detail is that spacecraft don't usually run on pure oxygen at normal Earth pressure. Early programs experimented with different approaches, and there were hard lessons that made everyone more respectful of fire. These days, most long-duration habitats use a mixed gas atmosphere closer to what you're used to, managed by sensors that watch partial pressures the way a careful person watches their bank account right before rent is due. Oxygen can be stored as high-pressure gas, generated chemically, or produced by splitting water. That last one is the most satisfying because it feels like a neat trick, and it is. Electrolysis takes water and uses electricity to separate it into hydrogen and oxygen. You keep the oxygen for breathing, and you do something with the hydrogen so it doesn't become an annoying roommate. On the International Space Station, hydrogen can be combined with carbon dioxide in a Sabatier reactor to make water and methane. The water can go back into the loop, and the methane is typically vented. It's a strange kind of alchemy. You exhale carbon dioxide, the system pulls it out, reacts it with hydrogen, and gives you back water that can become oxygen again. You're basically breathing through chemistry. It's not perfect, and it's not effortless. Machines need maintenance. Filters saturate. Valves misbehave. Pumps get tired. But as a concept, it's soothing. The station doesn't depend on endless deliveries of oxygen the way a camper depends on endless trips to the store. It makes what it needs by continuously rearranging matter. Carbon dioxide removal is its own quiet art. On some missions, it was handled with lithium hydroxide canisters, consumable scrubbers that chemically bind CO2. They work well, but they're not exactly sustainable for months and years because each canister is a one-time favor. Long-duration habitats prefer reg-interval systems, like molecular sieves that adsorb CO2 and then release it when conditions change so the material can be reused. Adsorption is one of those words that looks like it's trying too hard, but the idea is simple. Certain materials act like a sponge for specific molecules. When the sponge is full, you squeeze it out by heating it or changing pressure, and you're ready again. All of this means your sleep in space, if you were there, would be accompanied by a background soundscape of fans and pumps. People sometimes imagine space as silent, and the vacuum outside is silent, but inside a spacecraft, it's more like living in a gentle machine room. Air must be circulated constantly, because in microgravity, warm air doesn't rise and cool air doesn't sink the way it does on Earth. Exhaled CO2 doesn't automatically drift away from your face. It can form a small cloud around you if airflow is poor, which is an unsettling thought until you remember that engineers are extremely motivated to prevent carbon dioxide halo around the head as a lifestyle. So ventilation is continuous. Air is pushed through filters, across sensors, around corners, into every module and sleeping nook. Those fans are the unsung lullaby of long missions. They also prevent pockets of stagnant air, where humidity could condense and invite mold to start acting like it paid rent. Water is even more personal. On Earth, you treat water like it's everywhere until it suddenly isn't. In space, water is always a strategy. You need it for drinking, for food, for hygiene, for cooling systems, for oxygen generation, and for being psychologically okay, because humans are not designed to feel dry as a permanent condition. The station's water loop is one of the most elegant, mildly uncomfortable facts in space exploration, and it becomes easier to love when you hear it with the right tone. A large portion of the water you drink has been recycled from humidity in the air and, yes, from urine. You can let your inner 12-year-old giggle for a second, quietly, because people are trying to sleep, and then you can appreciate the engineering. The urine is processed through a system that separates water from dissolved solids, often by distillation techniques adapted for microgravity. Moisture from breath and sweat is condensed from cabin air and added to the pool. Everything is filtered through multiple stages, including activated carbon, ion exchange, and microbial control, until it meets strict standards. The result is not gross water. It's water that has been cleaned so thoroughly it can be cleaner than what comes out of a kitchen tap in a lot of places on Earth. The emotional barrier is mostly cultural. Chemically, it's a triumph of closed-loop thinking. The molecules don't care where they've been. They care what they are right now. If you want the quiet wonder version, you imagine a water molecule leaving your lungs as vapor, drifting into a condenser, becoming liquid again, passing through filters, joining the supply, being split into oxygen and hydrogen, and then returning to your body as breathable air. It's a circle that feels almost too neat, like a bedtime story that refuses to waste anything. Food is less circular, at least for now. Most space food is still delivered from Earth, packaged to last, designed to minimize crumbs that would float into electronics. Crumbs are tiny hazards in microgravity because they don't politely fall onto a plate. They roam. They find crevices. They join the dust problem you were just admiring from the outside, except this time the dust is from your crackers and it's living inside your spacecraft, which is less poetic. So foods are engineered. Tortillas replace bread in many contexts because they don't flake as aggressively. Seasoning behaves differently because fluids don't settle on your tongue the same way when your sinuses are a bit congested from microgravity shifting fluid upward in your body. People report that taste can feel muted, so spicier sauces become popular. It's funny and kind of human. You can travel beyond Earth and still end up missing something as basic as flavor that feels right. The body itself becomes another environment to manage. Microgravity changes how fluids distribute. Blood and water shift toward the head. Faces look puffier, legs look thinner, and your body starts behaving as if it's in a weird, permanent head tilt. Your vestibular system may protest at first because it's used to gravity as a constant reference. Eventually, many people adapt, But the adaptation itself is a reminder that your senses are not truth detectors. They are pattern detectors, and in space, the patterns change. That's where the gentle sarcasm slips in. Humans are impressively adaptable and also hilariously dramatic about it. Give us a new environment, and we'll learn it, but we'll complain for a while first, because that's tradition. To keep muscles and bones from weakening, astronauts exercise. A lot. Not as a hobby, but as maintenance. Your body normally loads bones and muscles simply by being upright. Remove that load, and the body starts economizing in the laziest way possible. Bone density can decrease, muscles can shrink, and cardiovascular conditioning changes. So the spacecraft includes a gym, which is a sentence that still feels surreal. Treadmills with harnesses to pull you down, resistance devices to simulate weights, stationary bikes, machines that keep your body reminded of what effort means. Even sleep becomes a managed system. In microgravity, you don't need a mattress. You need a place to anchor yourself so you don't drift into a wall or float nose first into a panel. People often sleep in small compartments or sleeping bags attached to a surface, with ventilation directed to ensure good airflow. That airflow matters not only for comfort, but because exhaled CO2 must be carried away. Your sleep, if you were there, would be held by straps and zippers and the steady hum of fans. The idea isn't claustrophobic when you picture it correctly. It's cocoon-like, controlled, safe. Temperature is kept within comfort ranges, but microgravity changes how you feel it. Without convection working the same way, a warm object doesn't automatically create rising warm air currents. Heat can form a thin boundary layer around you, and sweating doesn't evaporate as effectively if airflow isn't doing its job. The station's environmental control system keeps air moving, removes humidity, manages heat loads from electronics and humans, and routes waste heat to radiators that face the dark. Those radiators you imagined earlier aren't just for instruments. They're part of the human comfort system. Your body heat becomes a number in a thermal model. It's oddly comforting to know that even your warmth is accounted for. Then there's the invisible chemistry of trace contaminants. Humans release a surprising variety of compounds simply by existing: breath, skin, cleaning products, off-gassing from materials. A spacecraft is built with materials chosen for low outgassing, but nothing is perfect. So air revitalization includes activated carbon beds and catalytic oxidizers that break down certain compounds. Sensor monitor air composition. Engineers set limits for a range of substances because headaches and irritation are not helpful in a place where your nearest emergency room is an entire planet away. This is why spacecraft design can feel like the most extreme version of building management. It's the ultimate HVAC problem, except the building is moving at thousands of meters per second, and the outside environment is a vacuum, and the repair crew is also the residents. The psychological side is just as real, and it fits the sleep mood better than you might expect, because it's about routine. Humans do better with rhythms. So space missions lean on schedules: wake, hygiene, meals, work blocks, exercise, communications, sleep. Even with the sun rising and setting every 90 minutes in low Earth orbit, crews keep a consistent day so their bodies don't get confused. Light is used deliberately: brighter, bluer tones at morning, softer tones at evening. It's an artificial sunrise in a place where natural cues are chaotic. And for comfort, small things matter: a favorite drink pouch, a familiar song, a message from home, photos taped to a panel, a private moment in a tiny compartment. It's a reminder that space exploration is not only a technical project. It's a human project with human needs that remains stubbornly unglamorous. You can almost feel how everything you've heard so far links together. The whispering radio signals, the careful gravity slingshots, the shimmering blankets, the radiators that breathe heat into darkness, and now this. A closed-loop habitat where your breath becomes chemistry and your water becomes a cycle. The magnificence isn't in some dramatic speech. It's an steady fact that a fragile, thoughtful bubble of life can be sustained while the universe does its best to be uninhabitable. And as you settle into that thought, another quiet shift starts to happen in the story. The human bubble is stable enough that attention can drift outward again, toward places where air doesn't move at all, where dust behaves like a clingy rumor, and where the simplest act, like leaving a footprint, becomes a mark that might outlast civilizations. The bubble of air and recycled water fades behind you in your imagination, and what replaces it is a kind of honesty. No air flove, no soft diffusion, no forgiving blood. The moon doesn't do comfort by accident. If comfort happens there, it's because someone engineered it on purpose, and then someone else double-checked it, probably while whispering something like, "Please don't make me explain this failure in a meeting." You arrive at the surface, and the first sensation is not sight. It's absence. The silence isn't peaceful the way a quiet room is peaceful. It's absolute, the kind of silence that exists because there's literally nothing to carry sound. Your own movements become private. If you scrape your boot against lunar soil, nobody hears it outside your suit. If something falls, it doesn't make a satisfying clink. It just falls, obedient to gravity that is lighter than Earth's, but still firm enough to keep you honest. The sky is black even in the daytime. That's not poetic exaggeration. It's optics. With no atmosphere to scatter sunlight, there's no blue dome, no gradient, no haze. Sunlight arrives like a hard spotlight. Shadows are not gentle. They're ink. A small rock can throw a shadow, so dark it looks like a hole cut into reality. If you step from light to shade, it's like moving between two different worlds with no transition in between. Your eyes, used to Earth's soft diffusion, take a moment to accept this. On Earth, air helps. It scatters light, fills in shadows, makes distant objects fade. Here, distance doesn't fade the same way. A ridge far away can look crisp, almost too crisp because there's no atmospheric blur. Depth becomes harder to judge. The landscape tricks you with clarity. Something can look close and still be kilometers away, which is a delightful problem if you're enjoying the view and a less delightful problem if you plan to casually stroll over there like at a neighborhood park. The ground under you is not sand, not soil, not anything that has ever been alive. It's regolith, crushed rock and glassy fragments produced by countless impacts over billions of years. Because there's no wind and no rain, the moon's surface isn't being rounded and softened. It's being pulverized. A meteoroid hits, rock shatters, the fragments scatter, and then they just stay. Over time, the surface becomes this fine, sharp dust mixed with larger broken pieces, like a beach that never learned how to be smooth. It's also slightly clingy, which feels like an understatement once you've seen it. Lunar dust is notorious because the grains are jagged and electrostatically charged. Without an atmosphere, the surface gets bombarded by sunlight and the solar wind, and that interaction can charge dust particles. They can stick to suits, gloves, tools, anything. They cling like they're emotionally invested in coming home with you. And once they do, they scratch. Those grains are abrasive enough to wear down seals and joints. Engineers treat dust like a quiet villain, not because it's dramatic, but because it's persistent. People who have been to the moon describe the dust as having a particular smell once it was brought inside and mixed with air, something like burnt powder. That detail always lands in a strange way, an airless world still leaving a scent in your memory, as if the place insists on having a signature even when it refuses to give you a breeze. You take a step and you see the footprint form with crisp edges. This is where the moon's weird gentleness shows up. Your footprint isn't going anywhere. There's no weather to erase it, no rain to soften it, no wind to scatter it. On Earth, even the best footprint is temporary. On the moon, your footprint is a stubborn statement. It will fade, eventually, but eventually is a word that means something different here. Micrometeoroid impacts will churn the surface over long spans of time. Thermal cycling, extreme heating during the long lunar day, extreme cooling during the long lunar night, can stress rocks and contribute to slow breakdown. Moonquakes happen too, driven by tidal forces and thermal effects, though the moon is far less active than Earth. Even with all that, the timeline is not your timeline. It's geological. The surface is like an archive that writes slowly and erases even more slowly. That's why the idea of history on the moon feels so literal. Tracks from rovers, the disturbed soil around landing sites, and the equipment left behind can remain recognizable for decades, potentially much longer, because the usual earthly erasers are absent. When orbiters photograph old landing sites, the visible traces feel almost eerie, not because they're spooky, but because they're still there, crisp against a world that otherwise looks untouched. It's like finding a handprint on a sculpture you expected to be ancient and pristine. Only the handprint is yours, and the sculpture is an entire world. The light itself tells stories. The moon rotates slowly relative to the sun, so a day on the lunar surface, sunrise to sunrise, lasts about 29.5 Earth days. That means 2 weeks of daylight and 2 weeks of darkness at many locations. 2 weeks of sunlight is not gentle warmth. It's sustained, direct exposure. 2 weeks of night is not cozy darkness. It's deep cold with no atmospheric blanket. In that environment, temperature control becomes a form of survival poetry. Spacesuits and landers have to manage heat not by convection, but by radiation and conduction. The same radiators you imagine dumping heat into darkness become essential again. Except now the darkness is inches away beyond a thin layer of insulation, and the stakes include your fingers and toes. In sunlit areas, you need to get rid of heat. In shadows, you need to preserve it. The balance is delicate, and the solutions often look like a mix of reflective surfaces, layered insulation, and careful plumbing for heat transfer, all designed so the person inside stays within an annoyingly narrow comfort range while the outside swings like a pendulum. And yet, walking there feels strangely calm. Lunar gravity is about 1/6 of Earth's, so your body becomes lighter, but not weightless. You still feel grounded, just less argued with. You can hop. You can lift things that would feel heavy on Earth. Your movements become more floaty, and if you're not careful, you can overdo it because your muscles still have Earth habits. That's the gentle comedy of it. Your brain keeps assuming gravity is the same, and the moon patiently proves you wrong. The suit adds its own personality. It's pressurized, stiff, and it resists bending the way a balloon resists being folded. Every movement is effort. You're not casually strolling. You're negotiating with a portable life support system that wants to remain a smooth sphere. The effort is real, and the calm comes from rhythm. Step, plant, shift, step. Your breathing becomes part of the soundtrack inside your helmet, and your own voice returns through your headset slightly altered, like you're speaking through a small, private cave of air. Unlike Mars, there's no meaningful atmosphere to slow you down if something goes wrong. A fall is a fall. A torn suit is an emergency of the highest order. That's why lunar exploration always carries an undercurrent of respect. Not fear in a panicky way, but respect in the way you respect the ocean when you're on a small boat. You can admire it, even love it, without pretending it's safe. Communication feels closer here, almost intimate compared to deep space. The moon is far enough that you're undeniably away, but close enough that the delay is only about a second and a bit each way. You speak, you wait a heartbeat, you hear the reply. It's just long enough to remind you that signals have to travel, but not long enough to turn conversation into a slow-motion ritual like it becomes on Mars. There's a sense that Earth is still within calling distance, even if you can't step outside without carrying your own air like you learned earlier. The horizon is also closer because the moon is smaller. Its curvature hides distant terrain sooner, giving the landscape a bowl-like quality. You can stand in a flat area and still feel enclosed by geometry, as if the world is gently curving away from you. Mountains don't look as towering in the same way because the scale cues are different. Craters dominate the scenery because impacts are one of the moon's main sculptors, and some craters near the poles hide pockets of permanent shadow, regions that never see sunlight because of the moon's small axial tilt and the angles of crater walls. Permanent shadow is where the story turns quietly mysterious. In those cold traps, temperatures can be so low that water ice can remain stable for extremely long times. That doesn't mean the moon is an icy world in the cozy sense. It means it has hidden vaults where molecules can settle and stay, protected from the sun's relentless spotlight. The idea that an airless, sun-blasted world could still shelter frozen water in the dark is exactly the kind of contradiction space exploration loves. It's not loud drama. It's a secret kept by geometry. Those shadows are also dangerously cold. A tool left in shadow can become brittle. A battery can lose performance. Electronics can struggle. This is why future missions talk about managing light like a resource, using peaks near poles that catch near constant sunlight for power, while reaching into the nearby shadows for science and potentially for usable ice. Light becomes location. Darkness becomes location. On Earth, you walk into shade, and it's still the same day. On the moon, shade can be a radically different thermal universe. The surface itself is also soaked in radiation compared to Earth's protected ground. Without a thick atmosphere and a global magnetic field like ours, the moon is more exposed to the solar wind and cosmic rays. That doesn't mean every moment is instantly lethal, but it does mean shielding matters, timing matters, and long stays require thinking about protection in a way that feels both ancient and futuristic. Ancient because you're again building shelter against the elements. Futuristic because the elements include particles that can pass through you if you don't treat them with respect. Even the simple act of landing is its own dusty theater. When engines fire near the surface, the exhaust can kick up regolith and send it outward in a low-gravity spray. That dust can travel far because there's no air to slow it down, and it can sandblast surfaces it hits. Future landers are designed with this in mind. Landing pads, throttle strategies, site selection, maybe even prepared surfaces someday. It's another example of space exploration being forced into humility. You arrive with fire, and the ground responds with flying grit. And yet the gentler miracle remains. You can leave a mark here and expect it to persist. That's not vanity. That's physics. The moon preserves because it doesn't recycle the way Earth does. Earth is alive in its processes. Plate tectonics, erosion, weather, oceans, all of it constantly reworks the surface. The moon is quieter. It changes, but it changes slowly and mostly by impact and temperature, not by flowing water and wind. So when you imagine those early missions, the iconic scenes aren't only about flags or speeches. They're about the simple evidence of presence. Footprints, wheel tracks, disturbed soil, instruments placed carefully. Laser retroreflectors were left on the moon so that beams sent from Earth can bounce back, allowing precise measurements of the Earth-Moon distance over time. That's one of the most relaxing kinds of science. A quiet experiment that lasts for decades, performed by light itself. You send a pulse, it returns. You measure time. Time becomes distance. Distance becomes knowledge. No fireworks required. You stand there in the harsh light and deep shadow, listening to your own breath and the steady hum of your life support systems, and you feel the grandeur build in a different way than the launch pad did. The launch pad was a cathedral of thunder waiting to happen. The moon is a museum of silence where the exhibits are made of light, dust, and time. And after you've felt that, after you've watched your own footprint sit there with crisp edges like a signature, your curiosity naturally turns to the next kind of explorer, one that doesn't need air, doesn't complain about dust getting into its joints as loudly, and can take its time moving across a landscape where taking your time is not a flaw, but a survival strategy. The robots arrive with patience built into their programming, and Mars waits with its own slower, red-colored mysteries. Mars waits with its own slower, red-colored mysteries. And the first thing you notice is how the planet seems built to teach patience. Even the light feels patient. It comes through a thin atmosphere that can't quite decide whether it wants to be a veil or a window. The sky isn't black like the moon's. It often carries a butterscotch tint because fine dust hangs in the air and scatters sunlight in a way that feels almost like a permanent sunset. It's softer than lunar daylight, but it's not comforting in the Earth sense. It's quiet in a different way, quiet with wind. That wind is a small miracle. Mars has an atmosphere so thin that a breeze can feel almost symbolic, yet it still manages to move dust, shape dunes, and paint the landscape in slow strokes. The air is mostly carbon dioxide. The pressure is a fraction of Earth's, and your skin would not enjoy meeting it unprotected for even a brief, heroic moment. But that thin air is enough to make weather. Not weather that pampers you, more like weather that occasionally rearranges the furniture. And into that environment rolls a machine that never hurries because it can't. A Mars rover isn't a race car. It's a careful traveler with a boxy body, 6 wheels, and a personality made of checklists. It wakes up, checks its health, warms what needs warming, talks when it can, works when it should, and then rests. If Mars exploration were a vibe, it would be steady competence with occasional stubborn drama. The drama starts with distance. Mars is far enough that conversation becomes delayed. A rover doesn't get live instructions like a toy car. It receives a plan, sometimes a whole day's worth, and then it carries that plan out with the quiet seriousness of someone following a recipe that cannot be tasted until tomorrow. When it finishes, it sends the results back. Images, measurements, status reports, packaged into radio signals that take minutes to reach Earth. That delay changes your relationship with the rover. It turns it into a colleague rather than a remote control tool. You can't micromanage. You can only guide. So the rover learns to watch its own feet. On Mars, feet are wheels, and wheels have their own poetry. The tracks they leave behind can be the most human-looking mark in a place with no humans. A pair of parallel lines, a repeating pattern of cleats, a slight wobble where the terrain gave way. It's oddly intimate, like reading handwriting. That's why a single wheel track feels dramatic on Mars. It says, something moved here on purpose. And because Mars doesn't erase as quickly as Earth does, those tracks can linger, fading slowly under dust and time. The rovers themselves are built around an attitude system that's both elegant and unglamorous. The rocker bogie suspension. 6 wheels, linked in a way that allows the rover to climb over rocks and keep its body relatively stable, distributing load without needing springs like a normal vehicle. The design looks almost casual, but it's one of those solutions that feels obvious only after someone spends years proving it in labs and deserts. It's the kind of engineering that doesn't brag. It just keeps working. You can picture the rover approaching a small rock field. On Earth, a car would bounce or scrape or simply go around. On Mars, simply doesn't exist. The rover pauses and studies. It takes images, builds a little 3D understanding from stereo cameras, evaluates slopes and hazards. It decides whether the ground is safe, whether a wheel might slip, whether the path ahead will trap it in soft sand that looks harmless until it swallows your progress. Soft sand on Mars is one of the planet's favorite tricks. It's not malicious, it's just indifferent. A patch of fine material can behave like a trap because the rover's wheels are not heavy enough to punch through the way a heavier vehicle might. Low gravity means less normal force on the wheels, which can mean less traction. You think lighter should be easier, and Mars replies, you'd think that. That's why the rovers move slowly, really slowly. A good driving day might be a few tens of meters, or maybe more when conditions are right, but nothing about it feels rushed. The rover stops, checks its position, checks will slip, checks if the terrain is doing something sneaky. It takes another image. It moves again. The motion is careful enough that it becomes soothing. It's the opposite of doom scrolling. It's progress that respects reality. And the rover doesn't just drive. It does science the way a patient person does science. By looking, comparing, measuring, and then looking again because it never trusts the first impression. You watch it aim its cameras at a rock face. The images it sends can feel almost like postcards. Rusty plains, layered cliffs, pebbles scattered like someone tossed them by hand. But each image is also data. The rover sees textures that hint at ancient water, minerals that form in certain conditions, sediment layers that suggest rivers or lakes that existed when Mars was a very different planet. Mars offers clues, not confessions. The rover's job is to sit with the clues without forcing a dramatic conclusion. That patience extends to the rhythm of the planet itself. A Martian day, a sol, is about 24 hours and 39 minutes. That extra 39 minutes is just enough to slowly desynchronize a human schedule. Early rover teams famously lived on Mars time for a while, shifting their workday later and later to match the rover's sunlight and power needs. Imagine finishing your shift and realizing your body thinks it's morning because your job is aligned with another planet's sunrise. It's a gentle kind of disorientation. Not scary, just surreal. Mars doesn't just take your machines, it tugs your calendar. Power is another reason the rover feels like a careful traveler rather than a bold adventurer. Some rovers use solar panels, living on sunlight like a very dedicated houseplant with a PhD. Others, like Curiosity and Perseverance, use radioisotope power systems, converting heat from a decaying source into electricity, giving a steadier supply that doesn't panic during dust storms. Solar-powered rovers had to treat dust as both nuisance and fate. Dust settles on panels, reduces power, forces the rover to ration activities. Sometimes, dust devils, those whimsical little Martian whirlwinds, would pass nearby and clean the panels, giving the rover a sudden boost like a surprise gift from the planet. There's something almost funny about that. Your mission depends on a small whirlwind deciding to do you a favor. And when the planet doesn't do you that favor, you feel the slow consequence. You can remember a rover that kept going far beyond its planned lifetime, like it simply refused to take the hint. And you can also remember how even the most stubborn machine eventually faces limits. On Mars, seasons change, sunlight angles shift, dust storms grow. The rover adapts until it can't. The end often isn't explosive or dramatic. It can be a quiet silence after a long series of hard-working days. In a way, that's the most fitting ending for a machine built on patience. The rover's science tools feel like a small toolbox turned into a laboratory. Cameras, spectrometers, drills, brushes, lasers, each designed to answer a question without needing a human hand. The laser instruments are particularly satisfying to imagine. A rover can zap a rock from a short distance, creating a tiny flash of plasma, and then analyze the light emitted to infer the rock's composition. It's like the rover is tapping on the planet and listening to the tone, except the tapping is a focused beam, and the listening is spectroscopy that turns light into chemistry. Then there's drilling, which sounds simple until you picture drilling in low gravity with a robot that has to hold itself steady without pushing too hard. The rover braces, positions its arm, applies controlled force, and collects powder that can be analyzed. Sometimes it caches samples, sealing them in tubes like tiny time capsules. Each tube becomes a promise, a piece of Mars set aside for deeper study, possibly one day brought back to Earth. Even that idea is patient. It's not solve the mystery now. It's prepare the evidence properly. A rover's arm is another quiet marvel. It moves with deliberation, not because it's slow for drama, but because precision matters. You don't want to whack a camera into a rock because you got excited. The arm positions instruments close to targets, places tools gently, withdraws slowly. In videos, it can look like the rover is thinking, and that's not entirely wrong. The sequence of motions is planned, checked, and executed with the kind of calm that makes you trust it. The landscape around the rover tells its own story in layers. You see hills that look like frozen waves, dunes that shift, crater rims that hold shadows. You see rocks that have been sandblasted by wind over ages, leaving shapes that resemble sculptures. You see places where the ground has polygons from freeze-thaw cycles, hinting at ice in the soil and temperature swings that work like a slow, geological breath. Mars has gravity that's stronger than the Moon's, but still lighter than Earth's, so the rover's weight is reduced, and that affects traction, drilling, stability. The rover has to manage that with wheel design and careful driving. Wheels often have grousers, raised treads that bite into soil. The wheel material is chosen for strength and flexibility, but Mars can still punish it. Sharp rocks can tear thin metal. Long distances can wear patterns into wheel skins. Engineers watch wheel images like doctors reviewing X-rays, looking for cracks and changes, deciding how to adjust driving to extend the rover's life. Those decisions become tiny dramas played out over weeks. A route is chosen not just by where science looks interesting, but by where the rover can survive. A slope might offer amazing layered outcrops, but if the tilt risks a slip or stresses a wheel, the rover may go around. Mars is full of tempting shortcuts. The rover mostly says no. It doesn't get bored. It doesn't need novelty. It needs safety. That safety is also why rovers have hazard avoidance. They can detect obstacles, stop if a wheel is slipping too much, and sometimes autonomously choose a path within a limited range. Autonomy on Mars is not a sci-fi robot deciding to write poetry. It's a cautious assistant deciding whether the next 2 meters are smarter than the next 2 meters slightly to the left. And because communication is delayed, that modest autonomy is what keeps the rover from doing something impulsive that would take weeks to diagnose from Earth. When the rover sends images back, there's another gentle trick. The raw images can look different depending on how cameras interpret color and lighting. Mars is lit by a sun that's similar to ours, but the dust in the atmosphere shifts the light, and cameras are designed for science, not aesthetics. Teams process images to approximate what a human eye might see or to emphasize certain features. You can look at one set and think red planet, then look at another and see subtle browns, tans, grays, even hints of blue in the sky at certain times. Mars becomes less of a stereotype and more of a real place with moods. Those moods can change quickly with a dust storm. A storm doesn't need strong winds to be impressive. Thin air still lifts fine dust. The sky can dim, sunlight weakens, temperatures shift. A solar-powered rover treats that like an unexpected winter. It reduces activity, conserves energy, waits. A rover with a radioisotope generator continues more steadily. But even then, the environment matters for visibility, thermal management, and planning. The most hypnotic part is how all of this, the driving, the imaging, the drilling, the waiting, happens at a pace that ignores human impatience. Mars doesn't reward hurry. It rewards consistency. A rover can spend a full day doing what looks like nothing because it's checking systems, warming components, updating software, or waiting for a communication pass. Those are not wasted days. Those are survival days. And in that slow cadence, the grandeur builds in a quiet way. You realize the rover is not just exploring a planet. It's extending your senses across space. Every wheel track is an extension of your foot. Every image is an extension of your eye. Every spectrum is an extension of your curiosity. The rover becomes your proxy, moving carefully across a world that once may have had rivers, lakes, maybe even environments that could have supported life in some form. The rover doesn't shout about that possibility. It just keeps gathering clues with calm persistence. A single wheel track curls around a rock, and it feels like a sentence. The rover stops at a ridge, and the panorama it sends back feels like a pause. You can almost sense the machine's routine. Wake, check, move, study, transmit, rest. That routine is what makes it trustworthy. It doesn't depend on inspiration. It depends on process. And while the rover keeps rolling, day after soul, your mind starts noticing another thread connecting back to earlier parts of the story. The Moon preserved footprints because it doesn't erase quickly. Mars preserves tracks differently. Dust can soften edges, winds can redraw dunes, but traces can still last. A planet with weather still holds memory. It just edits it slowly, like an artist who keeps revising the same canvas over centuries. The rover's patient march continues, and the mystery deepens because Mars always does that. Every answer creates a new question. Why is this mineral here? What made this layer? Where did the water go? How did the climate change? The rover doesn't solve everything. It points, it hints, it invites, and it keeps moving one careful wheel rotation at a time, leaving tracks that say your curiosity is capable of crossing the void. The rover's tracks stay behind you like quiet handwriting on a planet that still has wind to soften the edges, and that softness makes you appreciate something else. There are journeys where even tracks disappear because the traveler isn't pressing into dust anymore. The traveler is pressing into distance itself. Mars feels far until you compare it to the dark beyond the outer planets. From there, Mars becomes a warm, nearby thought, almost neighborly, while the real long road begins in a region where sunlight is thin and time starts behaving like a slow tide. The rover you are walking beside moves in meters. These next travelers move in billions of kilometers, and they do it with the same basic personality: careful systems, patient routines, and a steady refusal to hurry for anyone. Voyager is the name that sits in your mind like a low hum, not because it's loud history, but because it's the purest example of a mission turning into a slow, enduring relationship. Two spacecraft launched in 1977, built with 1970s brains, still speaking across a distance, so huge it makes your calendar feel like a short story. Picture them leaving Earth long ago, heavy with fuel and hope, and then picture them after the planets have done their slingshot work. After Jupiter's gravity bent their paths, after Saturn's gravity gave them their final push toward the outer dark. After that, the rockets are out of the story. There's no dramatic propulsion anymore. There's only glide and correction and a kind of cosmic coasting that feels like the ultimate relaxation technique. The part people forget is how cold and practical their survival is. There's no solar panel out there doing heroic work, because sunlight has become too faint to be useful in the usual way. Voyager runs on radioisotope thermoelectric generators, RTGs, which is a very long phrase for a very simple idea: a warm rock that slowly cools down over decades, turning heat into electricity with no moving parts. It's a little ridiculous when you phrase it that way, and it's also beautiful. A quiet lump of radioactive material produces heat as it decays, and thermocouples convert a fraction of that heat into electrical power. No sunlight required. No batteries that have to be recharged with rays. Just steady warmth and steady output, gradually declining over time as the decay continues. It's the closest thing spaceflight has to a candle that burns for half a century. That declining power is where the mission becomes strangely intimate. It stops being about spectacular images and starts being about choices. Every year, the RTG produces a bit less electricity, and the spacecraft has to live within a shrinking budget. You can almost feel engineers, decades apart, making decisions that resemble the ones in your own life. What stays on, what gets turned off, what can be sacrificed without losing the mission's meaning. Heaters are turned down. Instruments are powered off one by one, not because they failed, but because there simply isn't enough power to keep everything alive. The spacecraft becomes a minimalist by necessity, keeping only the systems needed to communicate and gather the most valuable remaining data. It's a slow shedding of complexity. Earlier you watch a rocket throw away stages to gain speed. Voyager throws away capabilities to gain time. And time is the real currency out there. The warmth that keeps Voyager alive isn't warmth you would feel with your skin. The surrounding space is close to absolute cold, and sunlight is a weak suggestion. Yet inside the spacecraft, that radioactive heat and a careful thermal design keep critical components from dipping below operational limits. Insulation still matters. Heat still moves. Radiators still decide what gets dumped into darkness. The same silent physics you met earlier on the shimmering blankets continues here, except the stakes are measured in decades. Communication becomes the lifeline that makes the whole thing feel almost personal. The spacecraft speaks to Earth with a transmitter that, by modern standards, is modest. By deep space standards, it's heroic. The signal leaves a dish antenna on the spacecraft and spreads out as it travels, expanding until it becomes a thin ripple in space. By the time it reaches Earth, it's faint, astonishingly faint, yet recognizable, as if the universe can't quite erase a well-made whisper. Down here, giant antennas listen. They don't just listen loudly, they listen intelligently. They know where to point, which frequency to expect, how to sift a pattern out of noise. They treat a few photons worth of radio energy like a precious letter arriving through a blizzard. That letter may contain not a dramatic confession, but a simple status, battery voltage, internal temperature, the behavior of plasma around the spacecraft. It's the calmest kind of drama where the protagonist simply remains alive. The distance builds slowly enough that you can feel it like a deepening breath. At the Moon, delay is a second. At Mars, it becomes minutes. For Voyager, it becomes hours one way. You could speak a sentence to Voyager, wait, and by the time a reply arrives, your tea has gone cold, you've forgotten what you said, and you started thinking about whether a crocodile dung sunscreen would actually work in interstellar space, which is the kind of thought your brain produces when it has too much time and not enough gravity. That delay forces a kind of serenity on mission operations. No one can fix anything quickly. Commands are planned carefully, sent as sequences, and then everyone waits. If the spacecraft responds in an unexpected way, the diagnosis happens with slow patience, using sparse data and a deep understanding of old systems. It's the opposite of modern troubleshooting where you reboot and pretend it never happened. Voyager can't be rebooted the way your laptop can. If something goes wrong, it becomes a puzzle solved by people who know their machine like a friend. And the machine keeps traveling outward, crossing thresholds that don't have fences but do have meaning. One of those thresholds is the termination shock, where the solar wind, charged particles streaming out from the sun, slows down as it begins to interact with the interstellar medium. Beyond that is the heliosheath, a region where the solar wind is turbulent and compressed. And then there's the heliopause, the boundary where the sun's influence yields to the pressure of interstellar space. These are invisible borders, but they show up in measurements. Changes in particle densities, shifts in magnetic fields, variations in cosmic ray intensity. The idea that the solar system has a kind of bubble around it is quietly comforting. You live inside the sun's atmosphere stretched across space, inside an extended environment that shields you somewhat from the harshest cosmic rays. You don't notice it day to day because Earth's own magnetic field and atmosphere do most of your local shielding work. But out where Voyager travels, that larger bubble becomes measurable. The spacecraft becomes a fingertip pressed against the edge of the sun's reach. When Voyager crossed into interstellar space, it didn't see a sign. It didn't witness fireworks. It simply recorded changes that suggested it was no longer in the solar wind's domain. The transition was scientific, not cinematic. That's part of why it feels so perfect for sleep. The universe doesn't celebrate, it changes state. And Voyager, still warm in a cold sea, keeps sending those state changes back as radio whispers. There's a specific kind of awe in knowing that the spacecraft is now sampling interstellar plasma, listening to the faint song of a medium that fills the spaces between stars. Plasma waves, particle counts, magnetic field readings. These are not visuals that flood your imagination with color, but they are facts that make your mind widen. The space between stars is not nothing. It has structure, density, and behavior. It is a place with properties, and Voyager is reporting from it. It's almost funny, in a gentle way, that one of humanity's farthest travelers is not a sleek modern design, but an artifact of late 20th century engineering. It carries instruments built with constraints that would make a modern smartphone laugh itself to sleep. Its computers are primitive by today's standards, yet the mission proves a calmer truth. Capability isn't only about raw power. It's about robust design, careful planning, and the willingness to accept a slow pace. Slow pace is what makes Voyager's goodbye feel long and warm rather than sudden and sad. The spacecraft didn't vanish. It didn't end with an explosion. It simply continued, year after year, farther and fainter, while people kept listening. The goodbye is a gradient. It's a long dimming, a sunset that takes decades. And it isn't only a scientific mission. Voyager carries an object that feels like a quiet human gesture, the golden record. It's easy to talk about it like a message to aliens, but the more soothing interpretation is simpler. It's a time capsule. It's humans admitting they are fragile and curious, and perhaps a little dramatic, and then deciding to package some of that into a durable artifact and attach it to a machine that might outlast the species that built it. The record contains sounds and images, greetings, music, pieces of Earth meant to represent life. Even if nobody ever finds it, the act of making it mattered. It's the kind of act you do when you want the universe to know you were here, but you also know the universe might never answer. That combination, hope without demand, is a surprisingly calming stance to hold. The farther Voyager goes, the more it becomes a lesson in quiet endurance. Its power fades slowly. Its instruments narrow down to the essentials. Its transmitter continues to speak, but with an ever more fragile margin. The big dishes on Earth continue to listen, but sometimes they have to allocate time among many missions. There are schedules. There are trade-offs. There's the practical reality that even the romance of deep space has to share antenna time. Yet the relationship persists. You can picture a night in the desert at a deep space listening station. The dish moves slowly, almost ceremonially, tracking a point you can't see. The air is cool. The stars overhead are sharp. Somewhere in the control building, a signal emerges from noise, and on a screen you see a line of numbers that mean it's still there, still traveling, still warm enough to function, still disciplined enough to do its job. That's a kind of comfort you don't get from fast stories. Fast stories end. Slow stories become part of the background of your life, like the sound of a fan in the dark. And while Voyager drifts, it also changes your sense of exploration. Up close, exploration looks like wheels and dust, careful moves across a crater rim, the rover pausing to study a rock like it's a clue in a long mystery. Far away, exploration looks like sustained trajectory, patient power management, and a signal that grows fainter while the meaning stays strong. The grandeur isn't a contrast. A tiny machine built by humans who never expected to see it reach interstellar space in the way it has continues to work. The universe is vast, indifferent, cold. The spacecraft is small, warm, stubborn. It keeps going. And that stubborn warmth starts guiding your attention toward another kind of warmth, the warmth of light itself, traveling through time. Because they're explorers that don't roll on wheels and don't coast beyond planets. They sit in carefully engineered darkness and catch ancient photons, the oldest messages of all, arriving from places so far away that Voyager's distance feels like a walk to the end of the street. Ancient photons arriving at your doorstep is the gentlest version of a cosmic event you will ever experience. Light does not announce itself. It ends its journey quietly, as a tiny touch on a detector, as a subtle electrical pulse, as data that turns into meaning only because someone cared enough to build a listener. Compared to Voyager's faint radio whisper, it's the same relationship in a different language, a long voyage, a fragile signal, and a receiver on Earth that refuses to stop paying attention. A space telescope is an explorer that doesn't chase. It waits. It holds still in a place where still is an engineering achievement, and it collects the universe one patient photon at a time. Waiting, in this context, is not a delay. Waiting is the method. From the ground, the atmosphere is a gift to lungs and a nuisance to optics. Air swirls and bends light, making stars twinkle and images blur. It blocks large parts of the spectrum, and it glows in infrared simply because it is warm. If you want a darker sky and cleaner starlight, you go above the air into an orbit where turbulence can't smear your view. That's the quiet genius of Hubble. It orbits Earth, close enough in cosmic terms that it still feels like it should be part of your neighborhood, just one that moves at several kilometers per second. Up there, stars stop shimmering into fuzzy halos. They become crisp points. Galaxies sharpen. The sky looks calmer, and that calm becomes information. Hubble's primary mirror is about 2.4 meters across. But the true marvel is how precisely it can point and how long it can hold its aim without wandering. With that steadiness, it can stare long enough for faint light to add up into something you can actually see. The deep fields are the purest proof that empty often just means faint. A patch of sky chosen because it seems unremarkable turns into a portrait of thousands of galaxies. Some look nearby and familiar, with spiral arms and dust lanes. Others are tiny, reddish smudges, so distant that their light began traveling billions of years ago. The calm shock is that the universe did not suddenly become fuller. You simply learn how to look longer. There is something soothing about that kind of revelation. It doesn't hit you with noise. It unfolds. It tells you the universe can be immense without shouting, and that attention is a tool as real as any rocket stage. It also tells you that patience is not passive. Patience is active listening. Hubble's story carries a quietly human moment that makes the whole enterprise feel less like myth and more like craft. When Hubble first began sending images, they were blurred. The mirror had a tiny shape error called spherical aberration, microscopic in everyday terms, disastrous for precision optics. It was the kind of problem that makes professionals go very silent. The solution was equally human. Astronauts visited Hubble and installed corrective optics, effectively giving it glasses, and later servicing missions upgraded instruments and replaced components. Hubble became a long relationship rather than a single headline, a reminder that exploration isn't only about perfect beginnings. It's also about building something resilient enough to be improved. Because Hubble observes mostly invisible and ultraviolet wavelengths, its images often look like an intensified version of what your eyes might wish they could see. Nebulae become luminous veils. Star clusters look like scattered gemstones. Galaxies show crisp geometry and delicate dust. It's easy to forget those pictures or measurements. The beauty is a byproduct of disciplined data. Underneath the beauty, the deeper comfort is the physics of delay. Light has a speed limit. If a star is 10 light years away, you see it as it was 10 years ago. If a galaxy is a billion light years away, you see it as it was a billion years ago. Distance and time are braided together in every image. A deep field isn't just many galaxies in one frame. It's a stack of different eras layered along the same line of sight. Then the universe adds its own slow signature, expansion. As space expands, it stretches the wavelength of light traveling through it. Light from very distant galaxies arrives redshifted, shifted toward longer wavelengths. Photons that left their galaxies as energetic ultraviolet or visible light can arrive as infrared after billions of years of gentle stretching. The older the light, the more the universe is pulled on it. That stretching is why the earliest chapters of cosmic history increasingly live in infrared. To read those chapters, you need an observatory designed for infrared sensitivity, and you need it to be cold enough that the telescope itself doesn't glow louder than the faint signals you're trying to detect. Warm objects radiate infrared. A warm telescope becomes its own noise source. Sensitive infrared astronomy is, at heart, the art of staying cold and staying quiet. That is where the James Webb Space Telescope changes the tone of the story. Webb lives far beyond low Earth orbit, near the Earth, Sun L2 region, roughly 1.5 million kilometers away. The distance isn't for drama. It's for geometry. From there, the Sun, Earth, and Moon remain on roughly the same side of the spacecraft, allowing a single sun shield to block their heat and light while the telescope side stays pointed into the deep cold of space. Webb's mirror is larger than Hubble's, about 6.5 meters across, built from 18 hexagonal segments that unfold and align. Those segments are coated with a thin layer of gold because gold reflects infrared light extremely well. The mirror looks lavish in a way that feels almost mischievous. The universe's oldest light is being gathered by something that resembles a golden honeycomb, and the extravagance is purely functional. The sun shield is the part that's easiest to imagine as a quiet, protective gesture. 5 layers of thin film, separated and tensioned, each one reducing heat flow. Sunlight warms the outer face, layer by layer. The temperature drops until the telescope and its instruments can operate in deep cold. The shield is not decoration. It's the difference between hearing a whisper and hearing your own warm electronics. Webb's deployment was a long, delicate unfolding performed far beyond any chance of a quick astronaut repair. Structures extended, membranes tightened, mirror segments opened and locked. After that, the telescope settled into what it does best: stillness. Long exposures, patient returns of data, a routine of looking that is almost meditative. The images Webb sends back feel different because Webb sees infrared, which human eyes cannot. The data is mapped into visible colors, so you can interpret structure and chemistry. Those colors are translations, not tricks. They help you distinguish what is hotter or cooler, what is dustier, what regions glow in different wavelengths. You aren't being shown a fake universe. You're being shown a universe your biology never evolved to perceive. With that translated vision, Webb can study galaxies so distant that their light began traveling more than 13 billion years ago, when the universe was assembling its earliest large structures. It can peer into star-forming regions wrapped in dust, because infrared can slip through where visible light struggles. It can split light into spectra and read chemical fingerprints, patterns that reveal which atoms and molecules are present and under what conditions. The telescope doesn't just take pictures, it reads. The stillness required for this reading is its own kind of calm marvel. Pointing in space means controlling orientation to tiny fractions of a degree for long exposures, while small forces try to nudge you. Even sunlight becomes a gentle adversary. Photons carry momentum, so sunlight exerts a tiny pressure. It is minute, but minute matters when you're trying to remain motionless. Reaction wheels spin. Star trackers compare patterns. Guidance sensors correct. The universe pushes softly, and the telescope resists softly. Sometimes the universe helps in a way that feels almost considerate. Gravitational lensing. Massive objects such as galaxy clusters bend space-time enough to magnify and distort the light behind them. Distant galaxies can appear stretched into arcs, brightened, sometimes even doubled. It's not glass doing the bending. It's gravity shaping geometry. The cosmos provides its own magnifying glasses, and your telescope takes advantage, allowing you to see objects that would otherwise be too faint. All of this changes your idea of exploration. Not every journey requires wheels or engines. Sometimes exploration is building a listener and allowing the universe to arrive on its own schedule. A photon leaves a remote galaxy, crosses expanding space for billions of years, and ends its path by striking a cold detector on a telescope you built. A tiny signal becomes a line of data. Data becomes an image or a spectrum. You receive it and realize you are holding evidence of an ancient event. There's room for a little gentle sarcasm because it keeps off from turning stiff. Humans invented read receipts, and the universe has been sending messages for cosmic ages without once checking whether you're paying attention. It just keeps sending. The photons keep arriving. Your only job is to listen well. And the pattern loops back to Voyager once more. Voyager's radio signal spreads out and arrives as a whisper in noise, needing giant antennas and careful decoding. Ancient galaxies send light that arrives as a whisper in darkness, needing cold detectors and careful calibration. Different carriers, same relationship. Distance makes everything faint, and meaning comes from persistence. These observatories also aren't solitary heroes. They're supported by schedules, ground stations, software updates, calibration teams, and procedures written in the calm language of prevention. Hubble continues its steady orbit above weather and air glow. Webb maintains its cold posture behind its sun shield. Both spend their lives doing one disciplined act: holding still and collecting reality. After you've been staring into the oldest light you can detect, your attention naturally returns toward the nearer glow of Earth, because there are structures in orbit that do more than observe life from afar. They host it, a place where fans hum without stopping, where routines keep a small world stable, and where a window can frame the planet as something both familiar and impossibly delicate. The planet framed in a window is a strangely grounding sight because it doesn't look like a map anymore. It looks like a living object, slow and bright, turning beneath you with an indifference that feels almost kind. You're not in a telescope now, watching the universe arrive from billions of years away. You're inside a place that hums, a place where the most advanced thing about it is how ordinary it tries to feel. The International Space Station is often described as a floating laboratory, which is accurate and also slightly unfair, because it's also a floating household. A household that happens to be moving at roughly 7.7 kilometers per second, seeing a sunrise about every 90 minutes, and holding together through vacuum like it's not even a big deal. You drift into it in your imagination the way crews do. Not walking, but gliding, hand to hand, pushing gently off surfaces. Microgravity makes movement feel effortless until you remember that every push has an equal and opposite reaction. And then you learn to push like a person who wants to arrive where they're going instead of spinning like an enthusiastic puppy. The station has a sound. People who've been there describe it as a constant background of fans. It has to, because air must circulate, heat must be carried to radiators, and equipment must stay within safe temperatures. In this sense, the station is a lullaby written in engineering. The hum is not an accident. It's the sound of a habitat staying alive. And the station has a night routine that is more calming than dramatic. Night doesn't mean the sun is gone for long. It means the crew's schedule says it's time to sleep. The lighting can shift to softer tones. Workstation screens dim. Experiments that need human attention are paused or handed off to automation. The station becomes quieter, not silent, but quieter in the way a house gets quieter when everyone has decided to stop being productive. Sleep in microgravity is one of those concepts your brain tries to interpret with Earth habits and fails. There's no lying down in the ordinary sense. You can sleep upright, sideways, even with your face toward the ceiling or floor, because those words stop meaning much without gravity. Instead, you secure yourself in a sleeping bag attached to a wall, inside a small crew compartment if you're lucky. You zip in so you don't drift. Some people like their arms tucked, some let them float slightly. The body finds its own neutral posture, and it can look a little like a quiet, astronaut-shaped comma. The station's air circulation ensures you don't exhale a little cloud of carbon dioxide that lingers around your face. That's one of those facts that sounds mildly unsettling and then becomes comforting because you realize how thoughtful the system has to be. The station doesn't leave comfort to chance. It designs comfort and monitors it with sensors. If the airflow is wrong, it's not just stuffy. It becomes a measurable risk. So the fans keep their steady hum. Your breathing stays easy. Sleep stays possible. The station's darkness is also different. The windows can be covered, but if you leave a window uncovered during orbital night, the view is intense. City lights stitched across continents, lightning flickering inside clouds like silent fireworks, auroras forming luminous curtains. The beauty is quiet, but not subtle. It's like Earth is showing off without being asked. During bedtime, crew members often have small rituals. A message from home, a recorded video, a favorite playlist. A book, if you can keep track of it. Small objects are velcroed or tethered so they don't float away. The station has this constant theme of anchoring. Everything wants to drift, so you design your life around gentle containment. Pins are attached. Tools are attached. Food packets are attached. Your sleeping bag is attached. Even your thoughts become attached to routine. That routine doesn't exist only for comfort. It exists because the station is an ecosystem. It needs consistent maintenance the way a boat needs consistent maintenance. Except the ocean outside is vacuum. Filters must be changed. Water systems must be checked. CO2 scrubbers must function. Cooling loops must keep working. Batteries must charge and discharge smoothly as the station moves in and out of sunlight. Solar arrays must track the sun attitude control systems, must keep the station oriented properly. It's a lot of moving parts for a place that's supposed to feel stable. Stability is the achievement. The station's orbit is not a fixed pedestal. The upper atmosphere, thin as it is, still causes drag. Over time, the station loses altitude and needs reboosts, small pushes to raise its orbit again. These reboosts can be provided by visiting vehicles or the station's own systems, depending on configuration. The idea that a space station needs occasional boosts, like a sleepy person needs occasional coffee, is oddly relatable. The station, too, cannot coast forever without attention. Inside, research happens even at night because some experiments don't care about the crew's circadian rhythm. Microgravity allows scientists to study fluid dynamics without buoyancy-driven convection, to observe how flames behave without rising hot air, to grow crystals in environments with different sedimentation patterns. Biology experiments study how cells respond to low gravity, how microbes behave, how plants grow when up is no longer a reliable instruction. Materials experiments observe how alloys solidify when gravity doesn't help heavier components settle. These experiments can be surprisingly serene when you imagine them. Droplets forming perfect spheres, flames forming blue, round shapes, liquids behaving like they're freed from Earth's habits. The station also has to manage waste heat from all this equipment. Earlier you imagined radiators dumping heat into darkness like photons leaving the ship. Here the same thing happens continuously. Heat is moved through coolant loops to large radiator panels outside. Those panels face cold space, and the station sheds heat like a living organism sweating, except the sweat is infrared radiation and the skin is metal. What makes it feel cozy rather than clinical is the human layer. Astronauts decorate walls with patches and photos. They label storage spaces with practical humor. They create small corners that feel personal. In a place where every cubic centimeter matters, personal space becomes a concept measured in small privileges. A quiet place to talk privately, a favorite seat near a window, a routine cup of rehydrated coffee or tea. Water behaves as if it has become playful. In microgravity, droplets form spheres floating like tiny glass marbles. You can push them gently, watch them merge into a larger sphere, watch them wobble with surface tension holding them together. This isn't just a visual party trick, it's physics on display. Surface tension becomes dominant when gravity steps back. The station turns everyday things into demonstrations. The way a wet towel behaves, the way soap doesn't rinse the same way, the way you have to use no-rinse wipes and careful techniques to stay clean without letting water roam freely. Yes, hygiene is a theme, and it's handled with the calm realism of people who accept that life is life even in space. Showers don't exist in the usual sense, because free-floating water is not a spa feature. It's a hazard, so you clean with wipes and rinse-free products. You manage hair in ways that don't create floating strands. You capture crumbs and droplets. You keep the habitat clean because microbes, moisture, and sealed environments will happily make a mess if you let them. Food time on the station has a small warmth to it. Meals are prepared by adding water to dehydrated packets, heating some items, arranging them with Velcro so they don't drift. Crews often eat together when schedules allow, because shared meals are one of the easiest ways to feel human. The menu is designed for nutrition and shelf life, but also for morale. Familiar foods matter. Variety matters. Small treats matter. A certain sauce or seasoning can become a hero because taste changes in microgravity and strong flavors cut through. Exercise is still the daily maintenance you heard about earlier. On the station, it's also a psychological anchor. The treadmill has a harness so you stay down against the belt. The resistance machine simulates weightlifting. The cycle lets you sweat without drifting. The station's air system pulls moisture away because sweat doesn't evaporate as neatly. Exercise becomes a ritual. You strap in, you work, you cool down, you rehydrate, and your body remembers what effort is. All of this is coordinated with a schedule that treats time like a tool. Mission control and onboard crews plan activities with precision, balancing science, maintenance, exercise, and rest. There is room for surprises, hardware issues, schedule shifts, visiting vehicle operations, but the default is order. That order is not rigid for the sake of being rigid. It's protective. It ensures nothing essential is forgotten. The station also has visiting vehicles that arrive like quiet deliveries to a remote lighthouse. Dockings and berthings are carefully planned events. When a cargo vehicle approaches, the station's crew and ground teams monitor relative motion, verify systems, prepare capture procedures. There are moments of tension, but most of the time, the procedure is a calm execution of geometry. A vehicle arrives with supplies, food, experiments, spare parts, sometimes new crew. The station breathes a little easier because its budget of resources just got topped up. At night, after the bustle fades, the station returns to its steady hum. The crew floats into their compartments. The station continues to orbit. Outside, the solar arrays move slightly. Radiators keep shining heat into darkness. Antennas keep linking to Earth, passing data through relay satellites, bridging the void with radio whispers. You can sense the continuity. Launchpad discipline, deep space signals, thermal blankets, life support loops, footprints on airless dust, rover tracks in red soil, and now a floating city where ordinary life is held together by extraordinary design. One more window glance, and Earth slides by beneath you, calm and bright. It's easy to feel small here, but small doesn't have to mean powerless. Small can mean precise. Small can mean careful. Small can mean capable of building a habitat that stays stable while moving through darkness. And stability depends on time. Time measured not just in clocks, but in the pulse of navigation systems that know exactly where you are by measuring seconds so precisely that distance becomes a consequence. The same obsession with timing that makes radio whispers readable becomes the key to finding your way anywhere in space at all. Timing becomes your quiet superpower because in space, position is never just where, it's when. The station gliding over Earth feels stable, but its stability is really a math spell held together by clocks, radio waves, and an obsessive refusal to be even slightly late. You can feel it in the simplest thought experiment. If a radio signal leaves an antenna and returns after a known delay, that delay is distance wearing a disguise. Light moves so fast it feels instantaneous in daily life. Yet once you're measuring in kilometers and millions of kilometers, even light has a schedule, and schedules can be measured. That's the first soothing fact about navigation. A spacecraft can be found by listening to time. On Earth, you have GPS to do the heavy lifting for you. Your phone acts casual about it, like it's not literally doing relativity corrections while you're looking up coffee shops. GPS works because satellites broadcast very precise timestamps, and your receiver measures how long each signal took to arrive. Multiply that travel time by the speed of light, and you get a distance to each satellite. With enough satellites, those distances intersect to reveal your position and your clock offset. It's geometry powered by time. It also contains a quiet cosmic joke. GPS needs relativistic corrections because the satellites are moving fast and sitting higher in Earth's gravity field than you are. Their clocks drift differently compared to clocks on the ground. If you didn't correct for that, your position would drift by kilometers per day. So every time your phone finds your location accurately, it's because engineers politely negotiated with Einstein in the background and then made it boring on purpose. Space navigation beyond Earth builds on the same idea, but stretches it to absurd elegance. Deep space missions rely on Earth-based antennas, those giant listening dishes, to send signals and receive replies. A spacecraft transponder can turn around the signal and send it back. Earth measures the round-trip light time. That gives range. Meanwhile, the frequency shift of the signal, Doppler shift, reveals the spacecraft velocity along the line of sight. Range and Doppler together are like a slow heartbeat monitor for a mission. They don't show you the spacecraft as a dot on a screen out there in space. They show you a relationship between Earth and the spacecraft, measured in time and frequency, again and again, until the trajectory becomes known with surprising precision. Even the weighting becomes part of the accuracy. The longer you track, the more your model refines. Noise averages out. Patterns become clearer. It's patient listening yielding a sharper map. There's also a technique that feels like a very calm form of triangulation. Observing the spacecraft's position against distant quasars using multiple antennas on Earth, then comparing arrival times of the spacecraft signal at those antennas. This can refine angular position on the sky. It's like using Earth itself as a giant measuring tool, stretching your baselines across continents so you can point better into the dark. Pointing is a huge deal because a spacecraft isn't only where it is, it's also where it's facing. If your antenna beam is narrow, as it often is in deep space, you have to aim like you mean it. And you aim using stars. Star trackers are essentially small cameras paired with catalogs. They look at a patch of sky, recognize star patterns, and infer orientation with quiet confidence. That means even when you're far from Earth, your reference frame is still the sky itself. The stars become your compass, not as poetry, but as an actual sensor input. The feeling of that is oddly comforting. You don't have to carry north with you. You just carry a camera and a catalog, and the universe supplies the landmarks. To know where you're going, you also need to know where everything else is going. Planetary positions aren't guessed. They're predicted with ephemerides, highly refined models built from decades of observations, radar ranging, spacecraft tracking, and careful celestial mechanics. When mission planners talk about targeting a flyby corridor at Jupiter or threading a gap near Saturn's rings, they aren't relying on vibes. They're relying on a solar system clockwork model that's constantly updated and stress-tested. Still, the system isn't perfect because the solar system isn't a frictionless diagram. Tiny forces accumulate. Solar radiation pressure gently pushes. Outgassing can nudge. Thruster misalignments create small errors. Even the gravitational pull of asteroids, tiny as it seems, can matter for extreme precision over long spans. For some missions, asteroid masses are refined because their gravitational tug affects the spacecraft's trajectory measurably. The cosmos doesn't just host your mission, it participates in it. And then there's the part that feels almost like science fiction, but is actually a calm idea in progress: navigating by pulsars. Pulsars are rotating neutron stars that emit beams of radiation. When those beams sweep past Earth, they arrive as pulses with stunning regularity. Some pulsars are so stable they behave like cosmic clocks. The pulses can be observed in X-rays or radio, and by comparing observed pulse arrival times to predicted ones, a spacecraft could infer its position in space, conceptually similar to GPS but using natural beacons instead of satellites. It's a beautiful thought. Instead of asking Earth where you are, you ask the galaxy. The reality is nuanced. Pulsar navigation needs sensitive detectors, careful models, and enough signal strength to be practical. Pulsars aren't all equally stable, and signals can be faint. But the concept has been demonstrated in space experiments, and it hints at a future where deep space vehicles could autonomously estimate their position without constant Earth tracking. Autonomy in navigation doesn't mean breaking up with Earth. It means giving the spacecraft a sense of direction when Earth is busy or far away. The same way a good hiker can keep moving even when the trail marker disappears. Autonomous navigation already exists in other ways. Rovers on Mars use visual odometry, comparing images of terrain to estimate motion and slippage. Spacecraft performing close flybys use optical navigation, tracking a target body against the star background to refine approach. You can picture a spacecraft approaching a small asteroid. The asteroid is a faint dot at first, then a brighter dot, then a shape. The onboard camera measures the dot's position relative to stars, feeding that into trajectory estimation, refining the aim point. The spacecraft becomes both traveler and navigator, watching the road while driving. It's not as romantic as trusting your instincts, but it's far more reliable. Even with all that autonomy, Earth-based tracking remains the backbone for many missions because Earth has the biggest antennas and the most computation and the luxury of stable infrastructure. Earth is the home base that can think in big loops. But even Earth's tracking depends on timekeeping that borders on obsessive. Atomic clocks matter because timing precision becomes distance precision. If your timing is off by a microsecond, your inferred distance is off by about 300 meters because light travels roughly 300 meters in that time. That's already too sloppy for many navigation tasks. Better clocks mean better ranging, better Doppler, better confidence. This is why deep space networks and navigation systems treat time like a sacred resource. Time is measured, compared, corrected, distributed. There are standards, calibrations, and constant cross-checking. The dream of controlling the heavens turns out to be mostly about maintaining clocks that don't get lazy. And there's more gentle irony. Time itself is not universal in the simple way your intuition wants. Velocity and gravity change how clocks tick. Deep space navigation accounts for relativistic effects, especially for the highest precision needs. Your everyday life doesn't notice those differences because the scale is small, but space missions notice because they can't afford not to. Space exploration is where relativity becomes quietly practical. No speeches, no philosophical debates, just corrections in the math so the spacecraft arrives where it needs to arrive. The station you were just drifting through runs on timing too. Its orbit is predicted and updated. Docking vehicles time their approaches. Rendezvous is choreography measured in seconds and centimeters, achieved through radar, optical sensors, inertial measurement units, and control laws that keep relative motion gentle. The dock itself is not a crash. It's a slow handshake. And that handshake depends on knowing precisely how fast and where, which means time again. You can feel the continuity across every environment you've visited in this story. On the moon, a footprint stays sharp because time passes differently there. Slow erosion, long memory. On Mars, a rover's track fades under dust and seasons, edited by wind. In deep space, Voyager's signal becomes fainter as time stretches across hours of light travel. In telescopes, ancient photons arrive from billions of years ago, turning time into a visible layer. And in navigation, time becomes the ruler you use to measure everything. Even the word mission elapsed time carries a comforting humility. It doesn't pretend time is infinite. It counts from a beginning and moves forward steadily, marking milestones with numbers that don't get emotional. In a control room, those numbers can feel like a heartbeat. T-minus, liftoff, stage separation, orbit insertion, cruise, flyby, landing, surface operations, extended mission. It's all time-stamped because without timestamps, the story becomes mush. There's also a psychological comfort in how navigation teams treat uncertainty. They don't pretend to know exactly where the spacecraft is as a single point. They represent it as an estimate with an uncertainty region. There's a nominal trajectory, and there's a covariance, a measure of how sure you are. Over time, tracking shrinks that uncertainty. Maneuvers can reduce it. Sometimes it grows if you go through a period without good tracking or if the environment adds noise. The goal is not perfection, it's control. And control is achieved by acknowledging what you don't know, then reducing it methodically. This attitude is a hidden reason space exploration feels calming when you listen closely. It is not a field built on reckless confidence. It is a field built on careful doubt. Doubt expressed as equations, tested against reality, updated when reality speaks back. It's the healthiest kind of skepticism, not cynical, just precise. You start noticing how many soft things in the story are actually hard in implementation. A whisper over radio needs immense antennas and coding. A gentle gravity assist needs years of trajectory design. A quiet telescope needs deep cold and precise pointing. A simple footprint lasting on the moon depends on the absence of atmosphere over billions of years. And just knowing where you are depends on clocks that are so stable they border on unnatural, which makes you appreciate your own ordinary sense of location in a new way. On Earth, you glance at a street sign and your brain does the rest. In space, there are no street signs. The street sign is time itself. The intersection is a set of numbers arriving at antennas. The map is a model that must be constantly updated. The compass is the star field recognized by a camera. You navigate by listening, and this listening extends beyond navigation into science itself. The same measurements that track a spacecraft can reveal a planet's gravity field. Slight changes in a spacecraft trajectory during orbit can map variations in mass distribution inside a planet or moon. The spacecraft becomes a probe in both senses, a traveler and a sensor. Gravity, again, is not just a force, it's information. When missions orbit the moon or Mars or other worlds, tiny Doppler shifts in the radio signal reveal tiny accelerations caused by gravitational anomalies, concentrations of mass, subsurface structures, differences in density. Those anomalies become maps. You don't dig into a planet to learn its structure. You watch how it tugs on a passing spacecraft. The planet reveals itself by the way it pulls. That idea carries a gentle grandeur. The universe is full of invisible forces, and you can infer them by patience, by timing, by listening to small changes and refusing to dismiss them as noise. And because you're listening, you also start realizing that the solar system is not just planets and moons. It is a network of trajectories, communications links, and timekeeping systems. It is a living geometry. That geometry becomes even more delicate when your target isn't a huge planet that kindly dominates the sky, but a small asteroid or a comet, an object with weak gravity, irregular shape, unpredictable surface, sometimes even jets that push it slightly as it warms. In those cases, navigation becomes more like approaching a drifting pebble in a moving river. You need exquisite timing and flexible planning. You need to accept that the target itself may behave like it has opinions, which is why the story is ready to shift again, away from stable orbits and toward encounters with small, ancient bodies that preserve early solar system history in a way planets cannot. The moon kept footprints. Mars keeps tracks. But asteroids and comets keep origin stories, cold, primitive material, wandering quietly, waiting for a visitor to arrive on a schedule written in clocks and gravity. Asteroids and comets don't feel like destinations the way planets do. Planets announce themselves with horizons, weather, and that comforting sense of down. A small body is more like a thought drifting through sunlight, tiny, ancient, and stubbornly uninterested in being visited. You don't arrive at it the way you arrive at a city. You match its motion, ease into its neighborhood, and try very hard not to bump it like you're parallel parking next to a priceless vase in total silence. From a distance, an asteroid can look like nothing at all, a faint moving pixel against a star field that refuses to cooperate. Up close, it becomes a world that never learned how to be round. Its gravity is so weak that surface is almost a polite suggestion. If you jumped, you might never come back down. If you tossed a tool, it could drift off into an eternal, low-speed retirement. It's the kind of place where the usual rules still apply, but they apply with such delicate force that your intuition keeps overreacting. And that delicacy is the point, because these bodies are time capsules. Asteroids are leftovers, material that never became a planet, fragments from collisions, rubble reassembled by gravity that's barely strong enough to call itself gravity. Many are primitive, meaning their composition has changed less since the early solar system. Their minerals and organic compounds preserve conditions from the era when the sun and planets were forming, when dust and ice clumped together and the solar system was still deciding what it wanted to be. That's why a mission to an asteroid can feel like a mission to the past, without the drama of time travel. You're not going back in time. You're going to something that has been keeping old chemistry in cold storage for billions of years, drifting quietly, waiting for a visitor with a clipboard and a lot of patience. The first strange part is orbiting. Around a planet, orbit feels stable, like a groove you settle into. Around a small asteroid, orbit can be fussy. The gravitational field is uneven because the body is irregular. The pull changes as you move around it. Solar radiation pressure can matter more than you expect, gently pushing the spacecraft as photons bounce off surfaces. Even the asteroid's own tiny gravity can compete with these subtle forces in ways that make simple orbit feel like a negotiation. So spacecraft often hover in controlled trajectories rather than commit to tight orbits at first. They map, they measure, they watch how the asteroid rotates, how sunlight hits it, how shadows move across boulders that look like they were tossed there by a sleepy giant. They build a gravity model by tracking slight changes in the spacecraft's motion, timing and Doppler again, turning tiny tugs into knowledge. They use cameras and LiDAR to create detailed shape models, turning a lumpy, spinning rock into a navigable landscape. When you finally see the asteroid close up, the surface can feel unexpectedly busy. It's not a smooth pebble. It's a mess of boulders, gravel, and fine regolith. Some asteroids are rubble piles, essentially a heap of material held together by weak gravity and friction, the reassembled remains of earlier bodies shattered by impacts. The fact that a rubble pile can exist at all is a quiet statement about the patience of gravity. Even a weak pull, given enough time, can gather fragments into something that counts as a world. And that world can surprise you. Bennu, for example, was expected to be smoother than it turned out to be. It ended up looking like a densely packed boulder field, as if someone had emptied a quarry into space and then gently pressed pause for a few billion years. Ryugu, visited by Japan's Hayabusa 2, had its own rugged personality. These missions made it clear that even the small worlds are not simple. They're complicated in the way real things are complicated, with history written into their shapes. Once you've mapped the target, the next step is the part that makes you hold your breath even though you're not the one doing it, touching the surface. Landing isn't quite the right word. In low gravity, landing is too dramatic. A spacecraft can't just drop onto the surface the way it would on Mars. It would bounce, possibly into space. So missions use touch-and-go sampling, brief contact, or carefully designed landers that can anchor themselves. The goal is to interact without committing to a full embrace. OSIRIS-RX did this at Bennu with a method that feels almost too gentle for a space mission. It approached slowly, using navigation based on images of the surface, matching landmarks, correcting its path with small thruster pulses until it was aligned with a chosen sampling site. Then it descended and extended a sampling arm with a collection head. The contact was brief. A puff of nitrogen gas stirred the regolith, lifting particles into the collection head. Then the spacecraft backed away. It didn't linger. It didn't press its luck. It touched, collected, and left like a careful person taking a single cookie from the tray and immediately closing the lid. That contact created a small cloud of dust, and the motion of that dust told its own story. In low gravity, dust doesn't fall quickly. It drifts. It moves with the gentlest pushes. You can imagine each grain as a tiny witness, floating lazily in sunlight, taking its time to decide whether it wants to return to the surface or keep wandering. Some grains did return slowly. Others may have escaped entirely. Either way, the event was less like digging and more like stirring a memory. Hayabusa and Hayabusa 2 used their own sampling approaches, including firing a small projectile into the surface to create debris that could be collected. Hayabusa 2 also deployed small hopping rovers and a lander. Hopping makes sense when gravity is weak. Wheels don't grip the same way. A hop can be a controlled move. It's a strange kind of locomotion, like the asteroid forces you to abandon your habits and adopt something more playful. Rosetta's mission to Comet 67P had a different flavor, because comets are not only small, they are active. As a comet approaches the sun, ice is warm and sublimate, releasing gas and dust in jets. Those jets can push on the comet like tiny thrusters, subtly altering its rotation and trajectory over time. They also create an environment of drifting particles around the nucleus, beautiful and hazardous at once. Rosetta managed to accompany a comet, staying near it for months as it moved through the inner solar system. That still feels like an impossible kind of companionship. A comet is an irregular, rotating body shedding material, and the spacecraft stayed close, adjusting constantly, mapping and observing. The images of 67P revealed a shape like a rubber duck, a lumpy two-lobed nucleus that looked stitched together. It didn't look like a pristine snowball. It looked like a rugged artifact that had lived a complicated life. Then there was Philae, the little lander that attempted to settle onto the comet's surface. Settle, again, is too optimistic. In that weak gravity, anchoring mattered, and the attempt became a lesson in how even gentle environments can produce surprisingly chaotic outcomes. Philae touched down, bounced, and eventually came to rest in a shadowed spot. It still sent back valuable data, still became a symbol of persistence, but the event reminded everyone that small gravity does not mean easy. It means the usual stabilizing forces are gone, and small errors can turn into slow, drifting consequences. This is where the engineering feels almost like choreography underwater. Everything must be slow and deliberate. Thrusters are used sparingly. Attitude changes are careful. The spacecraft's own motions can kick up particles, and those particles can affect sensors or even the spacecraft if they impact. The environment is delicate, and your presence disturbs it. That disturbance is scientifically valuable in itself. When you stir regolith, you learn about cohesion, grain size, electrostatic forces, and how material behaves in microgravity. You learn whether the surface is fluffy or compact, whether it responds like powder or gravel. Those details matter if you ever want to interact more aggressively, if you want to anchor, drill, excavate, or redirect. The sleepy beauty of a dust cloud also contains practical information about the physics of tiny worlds. And those tiny worlds behave in ways that are quietly dramatic over long timescales. There's a subtle force called the Yarkovsky effect. Sunlight warming an asteroid's surface during the day, and the asteroid re-radiating that heat as infrared later. Because the asteroid rotates, that re-radiated heat creates a small thrust. Tiny but persistent. Over years and decades, it can shift an asteroid's orbit measurably. It's one of the most relaxing facts in space dynamics because it's so gentle and yet so real. Sunlight doesn't only illuminate, it nudges. The universe applies pressure not with fists, but with warmth. For an object like Bennu, those subtle shifts matter because Bennu's orbit intersects Earth's neighborhood. Missions that study such objects aren't just doing curiosity science. They're also refining predictions, measuring the asteroid's shape, spin state, mass, and thermal properties so its future path can be forecast more accurately. It's the calm version of planetary defense. Not panic, just better numbers. Your mind can hold that without anxiety when you remember the scale of time. Orbits evolve over centuries. Predictions improve with data. The same discipline that keeps a spacecraft on course keeps long-term risk in perspective. It's not about fear. It's about understanding. And understanding is what sample return makes intimate. Bringing a piece of an asteroid back to Earth is more than a souvenir. It's a controlled transfer of ancient chemistry into labs, where you can measure with tools too large, too delicate, or too power-hungry to fly. You can cut samples, image their microstructures, analyze isotopes, look for organic molecules, study how water altered minerals long ago. You can compare results across teams in decades. A return sample becomes a library book that can be checked out by future scientists who haven't been born yet. That's a quietly thrilling thought. The mission ends, and the science continues. The capsule itself returns with its own gentle drama. Heat shield, atmospheric entry, parachutes, a landing in a planned desert area. A small object falls from the sky, carrying grains that predate your planet's oceans, and teams recover it with clean procedures designed to avoid contaminating the sample with Earth's modern biology and chemistry. It's almost humorous how careful humans become when handling ancient dust, like we're suddenly polite because the material is older than our entire species and deserves respect. Once the sample is in a lab, the mission becomes a different kind of journey. Under microscopes, researchers see textures and grains that tell stories about temperature, pressure, and chemical environments in the early solar system. Some samples contain hydrated minerals, indicating interactions with water on a parent body long ago. Some contain organic compounds that hint at the chemistry that can arise in space, the raw ingredients that could have been delivered to early Earth. The story becomes both cosmic and personal. You are made of atoms forged in stars, assembled into planets. And here's a small piece of that assembly process in a vial on a lab bench. It also loops back to your earlier sense of closed loops, air, water, recycling, life support chemistry, because sample return is another form of loop. Material leaves a small world, travels to Earth, is analyzed, and then changes how future missions are designed. Knowledge returns and becomes new trajectory plans, new instruments, new shielding, new confidence about how regolith behaves when you touch it. The loop is not only physical, it's intellectual. As you hold these small worlds in your imagination, you start to see how they connect the entire solar system story. Comets may have delivered water and organics to early Earth. Asteroids preserve early materials. Impacts shaped planetary surfaces. Dust and rubble are not just hazards. They're the building blocks that never stopped being present. The moon's regolith, Mars's dust, the micrometeoroids that pepper spacecraft, the boulder fields on Bennu, different expressions of the same ancient debris field that the solar system has been sorting for billions of years. And because these bodies are small, you also sense a certain vulnerability in them. A small push can matter. A gentle change in momentum can alter a path over time. That thought naturally leads to a broader question. If you can rendezvous with a rubble pile, map it, touch it, collect from it, and understand the forces shaping its orbit, could you also, one day, gently change its course if you needed to? The answer isn't shouted. It's approached the way everything in space exploration is approached, by testing, measuring, and doing one careful step that proves a bigger idea without turning it into a spectacle. That question, whether you could gently change an asteroid's course if you needed to, hangs in the air like a thought you can't quite set down. It's the kind of idea that sounds dramatic in a movie, but in real space engineering, it becomes almost domestic. Not casual, not careless, just methodical in the way you tighten a loose hinge before it becomes a bigger problem. Space has a way of turning big fears into small procedures. The first calming truth is that most asteroids are not secret threats hiding behind the moon, waiting for the perfect moment to ruin everyone's weekend. The solar system has been throwing rocks around for billions of years, and the modern approach is less panic and more inventory. Astronomers survey the sky, track objects, refine their orbits, and update predictions as new observations come in. It's like having a weather forecast, except the weather system is a rock that might swing by decades from now. The timeline alone takes the edge off. Even when the stakes are large, the pace tends to be long. And because the pace is long, the tools you use can be gentle. If you want to change an asteroid's future position, you don't need to shove it like you're moving furniture. You need to alter its velocity by a tiny amount. Tiny in the everyday sense, millimeters per second, centimeters per second, because over years, that tiny change accumulates. The asteroid doesn't need to be dramatically moved today. It needs to arrive at a slightly different place years later. The whole strategy is basically compound interest, except applied to momentum. This is the kind of physics that feels soothing once you accept it. The universe rewards small nudges applied early. It punishes late, frantic moves. That's why detection and tracking are such a big part of planetary defense. The earlier you know, the smaller the nudge required. So how do you nudge a mountain-sized rock that's been minding its business since before mammals learned how to be mammals? One straightforward method is a kinetic impactor. The idea is blunt but not chaotic. Send a spacecraft to collide with the asteroid at high speed, transferring momentum. No explosion required. Just a controlled hit at a carefully chosen angle and time. You don't need to pulverize the asteroid. You need to tap it in the right direction. The calming part is that space already does this naturally. Impacts happen constantly across solar system history. The kinetic impactor approach is essentially borrowing the universe's own behavior and doing it with paperwork. A real demonstration of this concept happened when a spacecraft deliberately slammed into a small asteroid moonlet to see whether its orbit could be changed measurably. That mission didn't try to save Earth in the cinematic sense. It tried to measure a controlled change in a controlled system. And it worked. The orbit changed, and the change could be tracked. That's important because planetary defense lives and dies on measurability. You don't want a plan that feels good. You want a plan that produces numbers you can verify. Even that collision isn't as violent as your imagination might insist. Relative velocities are high, yes, but in space you can hit something without creating an apocalyptic explosion. What you mostly create is ejecta, a spray of debris thrown off the surface, which can actually enhance the momentum transfer because the material leaving the asteroid acts like a recoil, a little extra push in the opposite direction. The details depend on the asteroid structure. Solid rock behaves differently than a rubble pile. Porous material absorbs energy differently. A loose surface might throw material off easily, or it might cushion the impact. This is why missions that study small bodies matter so much. Knowing whether you're tapping a boulder or a bag of gravel changes the plan. And still, the philosophy remains gentle. Change a little early. Another method is almost comically polite, the gravity tractor. Instead of hitting the asteroid, you park a spacecraft near it and let gravity do the work. A spacecraft has mass. The asteroid has mass. They attract each other. If the spacecraft hovers near the asteroid for a long time, maintaining position with thrusters, its gravity exerts a tiny pull on the asteroid, gradually altering its trajectory. The spacecraft is essentially towing the asteroid without touching it, like leading a hesitant dog with an invisible leash made of space-time. It's slow. It's patient. It's the opposite of dramatic. And that's why it's fascinating. The practical challenges are real. Hovering requires fuel. Maintaining a stable offset position near an irregular, rotating body is non-trivial. You'd have to choose a distance that provides enough gravitational influence while keeping the spacecraft safe from debris and uneven gravitational fields. But conceptually, it's one of the most relaxing ideas in all of space engineering. Nudging a cosmic object using the same gentle force that keeps you on Earth. There are other concepts too. Painting an asteroid to change how it absorbs and re-emits sunlight, using the Yarkovsky effect you already met as a subtle engine. Deploying a reflective solar sail near the asteroid to change solar radiation pressure. even using focused energy to gently ablate material and create a jet-like recoil. Some ideas live more in research and long-term planning than immediate deployment, but they share a theme. Most effective interventions are slow and deliberate, and slow is what space likes. All of this requires a level of knowledge about the asteroid that goes beyond "it's somewhere over there." You need to know its orbit precisely. You need to know its mass, shape, rotation state, surface properties, and internal structure. You need to know how it responds to forces, including sunlight and gravitational perturbations from planets. You need to understand uncertainty and reduce it. This is where the mood shifts from defense to understanding, which is the only way it ever really works. The better you understand the object, the less dramatic your response has to be. Uncertainty is what creates anxiety. Precision creates options. Tracking is an ongoing practice. Observations from telescopes refine orbital parameters. Radar ranging, when possible, can pin down distances and velocities with high accuracy. Space missions can fly by or rendezvous to measure directly. Every new data point tightens the range of possible futures. The asteroid's predicted path becomes less like a foggy cone and more like a narrow line. You trade fear for math. Even the word impact probability becomes less terrifying when you realize it's updated constantly. Early detections can have large uncertainties, leading to temporary spikes in predicted probabilities that later disappear as more data comes in. It's not the universe playing games. It's your knowledge improving. The most responsible response to an early, uncertain projection is not panic. It's more observations. And that process itself can be soothing. A community of observers around the world watching the same point of light, collecting measurements, feeding them into models, refining predictions. A quiet collaboration between humans and gravity. There's also a deeper comfort in scale. Earth has been hit before. Earth will likely be hit again on geological timescales. Yet the interval between truly catastrophic impacts is long compared to a human life. And the modern era is the first time a species has had the ability to see the objects in advance and consider a response. That shift from helpless to potentially capable doesn't need to be framed as doom. It can be framed as maturity. You're living in the era where we didn't know is slowly being replaced by we can track it, and tracking can be improved. Surveys are becoming more comprehensive. New telescopes scan larger areas of the sky more often. Infrared surveys can detect darker asteroids that don't reflect much visible light. Space-based observatories can look in directions difficult for ground telescopes, including regions closer to the sun's glare where objects can hide from nighttime ground surveys. The point isn't perfection. It's coverage. It's probability reduced. That reduction in risk isn't dramatic. It's statistical. It's the kind of progress that's easy to miss because it doesn't come with fireworks. But it's real. If a future mission ever had to nudge an asteroid, the planning would look less like a war room and more like a multi-year engineering program. You'd run simulations for many possible internal structures. You'd test materials. You'd design redundancy. You'd choose launch windows carefully. You'd target an impact point based on the asteroid's rotation and the desired momentum change. You'd measure results and adjust. It would be iterative. Space rarely gives you a single shot unless you insist on it. And that insistence is usually optional if you start early enough. There's also a quiet philosophical payoff. Planetary defense forces you to respect the solar system as a dynamic place. Orbits are not fixed. They evolve. Resonances can nudge objects over time. Small forces accumulate. Even planets migrate over very long timescales. The solar system is a slow dance, and asteroids are part of the choreography. In that dance, a small change can matter, which is both a caution and a comfort. A caution because it means you should measure carefully. A comfort because it means you don't need brute force to influence outcomes. You need timing. Timing again. It keeps returning like a steady refrain. In navigation, timing turns into position. In telescopes, timing turns into history. In planetary defense, timing turns into leverage. The earlier you act, the smaller the intervention. The later you act, the more you have to do, and space is not kind to rushed plans. So the most relaxing version of this whole topic is not the method itself. It's the timeline. A well-tracked object gives you time. Time gives you options. Options let you choose a gentle solution. If you imagine a spacecraft sent to an asteroid not as a weapon, but as a careful visitor, arriving, mapping, measuring, perhaps attaching a small beacon, perhaps performing a controlled tap, then the whole concept becomes less like a thriller and more like a maintenance task for the solar system's neighborhood. Like trimming a branch before it grows into a problem. It's still serious, but seriousness can be calm. Even the language changes when engineers discuss it. They talk about delta V and impact parameter shifts and uncertainty reduction. They talk about how many millimeters per second are needed and how far in advance. It's math that sounds almost mundane, and that mundanity is the point. Making something mundane is how you keep it controllable. And while that's happening, you remember that many asteroids aren't threats at all. They're resources of information, resources of material, and resources of curiosity. The same body you might one day nudge could also be a source of understanding about solar system origins. It could even, in a far future, be an object of mining interest. Not because anyone is eager to turn space into a quarry, but because some materials are abundant in small bodies and scarce on Earth. That idea opens a different path. Not defense, but relationship. Instead of treating asteroids as intruders, you treat them as neighbors you're learning to live with. That shift, fear into familiarity, is one of the quiet achievements of exploration. The unknown becomes known. The threatening becomes measurable. The measurable becomes manageable. And once a thing becomes manageable, your imagination starts reaching further because it always does. If you can send a mission to rendezvous with a rubble pile and gently change its trajectory, what else can you do with gentle, deliberate engineering? You can start thinking about traveling not only to objects, but to environments that are defined by fields and flows. Places where magnetic lines twist, where particles stream, where a planet's invisible shield shapes what reaches its surface. Those places are not out there in the cinematic way. They're around Earth right now. The space weather that hums through our magnetosphere, the solar wind that presses on our protective bubble, the auroras that ripple when the sun gets moody. Exploration isn't always outward. Sometimes it's into the invisible structure that surrounds your own planet, revealing that even home sits inside a larger, dynamic cosmic environment. You're thinking about Earth's invisible shield the way you think about a house at night. You don't stare at the walls, but you sleep better because they're there. The magnetosphere is like that, an unseen architecture wrapped around the planet, shaped by Earth's magnetic field and sculpted continuously by the solar wind, which is basically the sun's way of reminding you it never stops breathing. The solar wind isn't wind in the cozy, scarf-fluttering sense. It's a stream of charged particles, mostly protons and electrons, flowing outward from the sun in all directions. It carries the sun's magnetic field with it, stretched and twisted into an enormous spiral as the sun rotates. This field is called the interplanetary magnetic field, which sounds like a job title, and it behaves like one too. Always present, always influencing, always slightly in your way. Earth sits inside that stream like a rock in a river. The river pushes, the rock resists, and the boundary between them forms a bow shock, an actual shock wave in plasma, where the solar wind abruptly changes behavior. Behind that is a compressed, turbulent region called the magnetosheath, and beyond that is the magnetopause, the boundary where the solar wind's pressure balances Earth's magnetic field. It's the edge of your planet's magnetic bubble, drawn and redrawn every moment by a force you can't see. And the bubble has a shape. On the day's side, it's compressed. On the night's side, it stretches into a long magnetotail that can extend far downstream. The tail isn't empty. It's loaded with magnetic energy and particles, and when conditions are right, The tail can snap and reconnect its magnetic field lines in a process called magnetic reconnection. Snap sounds dramatic, but the effect is more like releasing tension in a stretched rubber band, except the rubber band is made of field lines, and the release is measured in particle acceleration and shimmering auroras. Auroras are where this invisible architecture becomes visible enough to feel like a gift. You see them from orbit first, because orbit gives you the best angle. Luminous ovals around the poles, shifting and curling, green and red, and sometimes purple, like the atmosphere is painting with electricity. From the ground, they can look like curtains or arcs, moving slowly as if they're thinking. The colors come from atoms and molecules in the upper atmosphere, being excited by energetic particles and then releasing light as they relax back down. Oxygen tends to give green and red. Nitrogen can contribute blues and purples. The physics is precise, the experience is hypnotic, and it's all driven by a conversation between the sun and Earth that never quite ends. Space weather is the name we give to the mood swings of that conversation. When the sun releases a burst of plasma and magnetic field, a coronal mass ejection, or when a fast solar wind stream catches up to a slower one, Earth's magnetosphere can be compressed and stirred. The auroras brighten. Radiation levels change. Currents flow in the magnetosphere and ionosphere. On rare, strong days, induced currents can even affect power grids on the ground. Space weather sounds like a headline, but in practice, it's a reminder that Earth is not isolated. It is immersed. This is where space exploration becomes subtly protective. Studying the sun and the magnetosphere isn't only curiosity. It's forecasting. It's learning to predict when the river gets rough. The missions that do this are some of the quietest heroes in spaceflight because they spend their lives measuring things you cannot photograph in the ordinary way. Magnetic fields, particle energies, electric fields, plasma densities. They sit in regions where they're constantly being buffeted by charged particles, and they simply keep measuring. The Magnetospheric Multiscale Mission, MMS, flies multiple spacecraft in a tight formation to catch magnetic reconnection in the act. That's an extraordinary sentence if you let it land. Multiple spacecraft moving together in space, measuring how field lines break and reconnect on scales so small and fast you need coordinated sensors to understand them. It's like trying to study a single ripple in a stormy ocean by putting 4 buoys in a precise geometric arrangement, then reading the subtle timing differences in what they feel. The payoff is understanding how energy stored in magnetic fields converts into particle motion and heat. It's also a weirdly calming kind of knowledge because reconnection is one of those processes that happens all over the universe, in solar flares, in planetary magnetospheres, in astrophysical jets. It's not local quirk. It's a universal behavior. By understanding it near Earth, you get a handle on a mechanism that shapes space throughout the cosmos. And Earth's magnetosphere isn't the only one worth admiring. Jupiter's magnetic field is enormous and intense, creating a magnetosphere so large it can dwarf the Sun in certain comparisons of size and scale. Jupiter's radiation belts are fierce, energizing particles to levels that make spacecraft designers treat the region with the same respect you'd give a storm with teeth. Missions that visit Jupiter have to use hardened electronics and careful trajectories. Even then, the environment is punishing. Yet Jupiter also has auroras that are magnificent and persistent, driven not only by the solar wind, but by the planet's rapid rotation and by its moon Io, which feeds material into Jupiter's magnetosphere through volcanic activity. Io is basically a cosmic troublemaker that supplies plasma, and Jupiter responds by lighting up its poles. It's a reminder that magnetospheres are not just shields. They're living systems shaped by internal rotation, moons, and solar conditions. Saturn has auroras too, more subtle with their own rhythm. Uranus and Neptune have magnetic fields that are tilted and offset from their centers, creating magnetospheres that are weirdly asymmetric, almost mischievous. Their auroras and plasma environments behave in ways that force you to drop the assumption that all planets are built like Earth. The universe doesn't do standardized designs. It does variations. Even Mars, which lacks a strong global magnetic field today, has remnants, localized crustal magnetic fields that create mini magnetospheres. Mars is more exposed, and its atmosphere can be stripped over time by interactions with the solar wind. Studying that process helps explain how a planet that may once have had flowing water could end up cold and thin-aired. It's the opposite of a bedtime horror story. It's a slow lesson. Environments change, and fields matter. You also start appreciating Earth's atmosphere as part of the shield system. The magnetosphere deflects many charged particles, and the atmosphere absorbs others. Together, they create an environment where complex life can exist on the surface without needing to live underground in permanent fear of cosmic rays. You might not thank the magnetosphere daily, but it's been doing its job continuously, like a security system you forget exists until you notice the world outside is not designed for you. This thought connects back to your earlier mental image of that fragile bubble inside a spacecraft. Life support systems create an Earth-like pocket in a hostile environment. Earth itself is doing something similar on a planetary scale. It maintains a pocket of habitability, not through intention, but through physics and geology and a magnetic dynamo in its molten core. It's a habitat built by nature, maintained by processes that have been running for billions of years, and still subtly vulnerable to the sun's moods. The sun becomes a character again, which is fitting because everything you've heard so far, from gravity assist to solar radiation pressure nudging asteroids, depends on it. The sun is a fusion engine, yes, but what makes it fascinating for space weather is its magnetic complexity. The sun's magnetic field twists, tangles, and reorganizes, driving sunspots, flares, and coronal mass ejections. It's not just a bright ball. It's an active plasma system with a heartbeat and occasional tantrums. And humans have decided to approach it. A mission like Parker Solar Probe goes closer to the sun than any spacecraft before, diving into the outer corona, the sun's atmosphere, where the solar wind is born and accelerated. The spacecraft doesn't touch the sun in the literal sense, but it enters regions where the sun's influence is intense enough that heat protection becomes a central character. Parker carries a heat shield that faces the sun like a calm, stubborn wall. Behind that shield, instruments measure magnetic fields, particles, and plasma waves. It's studying the birthplace of the wind that shapes your magnetosphere, tracing the chain from solar surface activity to the particles that eventually light up Earth's skies. And here's the gentle sarcasm your sleepy brain can enjoy. Humans built a spacecraft to approach a star, and the core problem wasn't, how do we survive radiation, as some dramatic monologue. It was, how do we keep the instruments cool enough to function while the front is being roasted? Space exploration loves turning epic ideas into extremely practical thermal management problems. Which brings you back, again, to those radiators and blankets you imagined earlier. Heat is a thread through everything. The sun provides energy that makes life possible, but it also provides energy that can fry electronics and boil propellant and charge dust grains on the moon until they cling to your suit like they've found their purpose. The solution is rarely to defeat the sun. The solution is to manage energy flows, reflect, radiate, insulate, route, and monitor. You can feel how this understanding creates a kind of calm confidence. The sun is active, Earth is protected, and humans are learning to predict the big changes. Space weather forecasting uses solar observations, sunspots, magnetic field measurements, coronagraph images of eruptions, and models of how disturbances propagate through the solar wind toward Earth. Satellites monitor the upstream conditions, so you get warning time before a strong disturbance hits the magnetosphere. It's not perfect, but it's improving. It's another example of turning uncertainty into manageable risk through patient measurement. And the science is inherently rhythmic. Solar cycles rise and fall over roughly 11 years. Activity increases, then decreases. Auroras become more common in active periods. Space weather events cluster. Then the sun quiets. That cycle is like breathing on a scale that makes your own breathing feel small. It's soothing to know that even the sun's chaos has patterns. All this invisible structure, the solar wind, magnetospheres, reconnection, radiation belts, also changes how you picture space. It's not just empty blackness between objects. It's filled with plasma, fields, waves, and particles. It's dynamic. It has weather. It has flow. Voyager is out there swimming in interstellar plasma. Webb is out there staying cold behind a sun shield. The station is out there inside Earth's magnetic bubble for much of its orbit, occasionally skimming regions where particle environments change. Everything is embedded in a medium. And because it's a medium, you can navigate it, measure it, and eventually use it. That last part is where the future quietly starts to glow. If you can understand magnetic fields and plasma interactions, you can design better propulsion systems that use electric fields and magnetic fields to accelerate ions, efficient engines for deep space cruising. You can design better shielding strategies for long missions, not just thicker walls, but smarter forecasting and operational planning that avoids the worst particle storms. You can plan routes and schedules that treat space, weather like mariners treated ocean weather, a factor to respect, predict, and work with. You can also imagine habitats beyond Earth that make their own shields, magnetic or electrostatic concepts that might one day reduce radiation exposure in deep space. These ideas are challenging, but the direction is clear. The more you understand the invisible structure of space, the less you treat deep space as pure hazard, and the more you treat it as an environment with rules. That shift is what makes the grandeur build. Space exploration started as reaching places. It becomes, over time, learning the conditions that connect those places, the fields, the winds, the timing, the energy budgets. It becomes environmental literacy on a cosmic scale. And with that literacy comes a new kind of curiosity. If the sun's wind shapes magnetospheres and habitability, what about other stars? What about exoplanets orbiting red dwarfs with frequent flares? What about worlds with magnetic fields strong enough to protect atmospheres, or without them, slowly losing their air? The moment you start thinking about habitability as fields plus atmosphere plus time, your attention naturally drifts outward to the planets around other suns. Not as a sudden pivot, but as a continuation of the same question you've been quietly carrying. How does life persist in a universe that is mostly hostile? And what does it take to build a stable pocket of comfort? Whether that pocket is a spacecraft cabin, an orbital station, or a planet with a magnetic heart. Other stars don't arrive in your mind like a sudden scene change. They come the way Voyager's whisper comes, faint and patient, and the way a telescope collects old light until it finally becomes an image you can trust. Earth's magnetic bubble still holds in the background of your imagination, flexing and relaxing under the solar wind. And beyond that is the space between stars, thin, cold, and quietly structured, filled with sparse particles and wandering fields that starlight has been crossing for longer than any human story. Somewhere out there, planets are moving through their own nights and mornings. They don't announce themselves. They hide inside their starlight, and you learn to notice them by watching for small, repeated changes that refuse to be random. A star dims by a fraction when a planet passes in front of it. The dip is tiny, clean, and stubbornly regular. You measure the depth and infer the planet's size compared to the star. You measure the spacing and infer the length of its year. With enough transits, the timing becomes dependable in a way that feels almost comforting. A shadow with a schedule, a world revealing itself through rhythm. Some planets reveal themselves through the star's movement instead. A planet tugs gravitationally on its star, making the star wobble in a tiny counterorbit. That motion shifts the star's spectral lines through the Doppler effect, sliding them slightly toward blue when the star moves closer and toward red when it moves away. The shift is so small it makes everyday precision look like guesswork. Yet it's enough to estimate the planet's minimum mass and to sense whether you're dealing with something rocky and dense or something puffier and more gas-rich. Then there are the rare one-time winks. Gravitational microlensing briefly magnifies a distant star when another star passes in front of it and bends the light. If the foreground star has a planet, the planet can add a quick extra bump in brightness, a signature that appears once and disappears forever. It's a method that refuses to be convenient, but it's generous in what it can reveal. Planets in wide orbits, planets far away, planets that don't often line up for neat transits. Every method is the same quiet habit in different clothing. You don't need to touch a distant world to know it exists. You read what it does to light. You let time do part of the work. When a planet transits, the story can become even more intimate because the light carries a hint of the planet's sky. A thin ring of starlight filters through the planet's atmosphere, if it has one, on its way to the telescope. Molecules absorb certain wavelengths and leave fingerprints in the spectrum. You aren't smelling alien air, but you are watching which colors are missing, and that absence becomes a kind of presence. Water vapor leaves recognizable patterns. Carbon dioxide leaves its own. Methane can show up too. Sodium and potassium can draw sharp lines like a quick signature. Clouds and hazes complicate everything, and that complication is oddly reassuring. A hazy atmosphere can mute features and make the spectrum look flatter, like a world that prefers soft lighting and refuses to be read too easily. That refusal is still information. It suggests aerosols, photochemistry, particles scattering light high in the sky. A planet can be mysterious in a scientifically useful way. Temperature adds another layer. Some planets are so hot that their atmospheres become an exotic chemistry lecture. Metal vapors, strange clouds, winds hauling heat from day side to night side. Others sit in gentler ranges where liquid water could exist on the surface if pressure and composition cooperate. That if matters. The phrase habitable zone is not a promise. It's a starting place where conditions might allow water to remain liquid, nothing more. A planet can sit at the right distance and still be dry, airless, frozen, or wrapped in an atmosphere too thick and hot to feel anything like home. Red dwarf stars make this puzzle especially delicate. They are common and long-lived, and their habitable zones are close in, which makes transits easier to see. They can also flare often, throwing energetic particles and ultraviolet light at nearby planets. Many close-in planets become tidally locked, one face in perpetual day and the other in perpetual night. That sounds like a harsh design until you remember atmospheres and oceans move heat. A thick atmosphere can circulate warmth. Winds can blur extremes. A twilight ring between day and night can become a place where conditions are steadier than your first instinct expects. This is also where the idea of signs of life needs the calmest restraint. It's tempting to want a single molecule to be a cosmic yes or no. Reality is gentler and more stubborn. Oxygen can be produced by life. It can also build up through non-biological pathways in some scenarios. Methane can be biological, and it can also come from geology. Even water is not a guarantee of anything beyond chemistry, doing what chemistry does. The honest approach is the one space exploration keeps choosing. Gather multiple clues, compare patterns, consider context, accept uncertainty, and keep listening. Direct imaging takes that humility and turns it into something almost meditative. Seeing a planet next to its star is like spotting a firefly beside a stadium light from far away. You need optics that can suppress glare with exquisite care, coronagraphs inside a telescope, or a separate star shade flying in formation to cast a precisely shaped shadow. When it works, the reward is a dot that isn't only a shadow maker. It shines with reflected or emitted light of its own. That dot can have colors. It can have brightness changes. It can hint at clouds, at hazes, at seasons in the broadest sense, the way a distant ocean might hint at itself by the way it reflects light. All of this still rests on the same practical thread you've followed since thermal blankets and radiators: steadiness. Telescopes stay cold so they don't drown faint signals in their own warmth. They hold still so delicate spectral features can build into clarity. They wait the way deep space antennas wait, letting a whisper arrive and then refusing to claim they heard more than they did. The grandeur doesn't need to shout. The night sky above your house is full of planets, and you can learn about them with nothing but patient light. You can compare them to Earth, not as a trophy, but as a working habitat: oceans and clouds, chemistry and climate, a magnetic heart that turns the solar wind into a luminous show at the poles instead of a constant assault at the surface. You've imagined life support systems humming inside a spacecraft. Earth is that idea scaled up by geology and time, maintained by processes that never ask permission and never pause for applause. Timescales have been the quiet lesson all along. Rockets live in minutes. Orbits live in hours. Rover tracks live in seasons. Voyager lives in decades. Deep-field photons live in billions of years. Habitability lives in eons. Your life sits on that ladder of time like a warm, brief rung. And brief doesn't mean insignificant. Brief can still be attentive. Brief can still listen well enough to turn a tiny dip in starlight into the knowledge that another world is out there, circling faithfully, keeping its own quiet schedule. The future of exploration, held gently, looks like better listening, quieter detectors, more stable platforms, smarter autonomy for deep space work, and perhaps small probes riding light pressure outward the way subtle warmth nudges asteroids over decades. The result won't be loud. It will be a calm update on a screen, a cleaner spectrum, smaller uncertainty, a planet that becomes more than a dot. A few images settle into place as the story eases. Voyager turning its dish homeward, still whispering. A station compartment with a steady fan hum, where sleep is possible because air is kept moving. A droplet of water floating, round and calm, refusing to fall because there is no down. A touch-and-go, sampling head stirring ancient dust, and a few grains drifting lazily into sunlight. Auroras painting invisible field lines into visible light, reminding you that even emptiness has structure. The pace softens further, not because anything ends sharply, but because the cosmos prefers long fades. Spacecraft continue until they don't. Telescopes continue until they don't. Photons keep arriving either way. You don't have to hold any of it tightly tonight. It can sit around you like a wide, dim room with a comfortable temperature and no urgent corners. Breathing stays steady and simple, a private metronome that doesn't need calibration. The soft background hum in your room stays gentle, an echo of life support systems and thermal loops, and comfort becomes what it has always been: balance maintained quietly. Earth keeps turning beneath its thin air without asking anything. The magnetosphere keeps holding and stretching and relaxing. The moon keeps its footprints in silence. Mars keeps its dust and its patient tracks. The solar wind keeps flowing and starlight keeps traveling, and none of it demands anything from you in this moment. Thoughts can become smaller without losing their truth. A single photon traveling for billions of years ends quietly in a detector. A single radio wave traveling for hours ends quietly in an antenna. A single breath ends quietly in your chest. The universe has always been comfortable with quiet endings. The darkness behind your eyelids is not empty. It's simply unlit, a gentle screen where the mind can place one last calm scene. A distant star, a soft, precise dip in brightness. A planet passing like a slow shadow. The rhythm repeats with patient certainty, and regularity becomes its own kind of kindness. Words soften. Sentences lengthen. Nothing needs to be solved tonight. Nothing needs to be chased. The sky will still be there when you wake, full of signals that never hurry and never resent waiting. Curiosity can rest without breaking. Questions can float without needing answers. You're allowed to be small inside something enormous. You're allowed to be quiet inside something endlessly active. You're allowed to close your eyes while the universe keeps doing what it does, steady, lawful, and in its own way gentle. Exploration, at its calmest, is simply attention. You gave attention to the quiet parts, the slow coasts, the faint whispers, the soft shadows, the invisible shields. That attention is enough. The room remains. The hum remains. Your breathing remains. The universe remains, unimaginably large and entirely comfortable with silence. And the last line settles almost like a whisper.